While you were sleeping, the laws of physics may have changed. Not violently, not loudly, not in a way that would wake you. No stars exploded, no atoms shattered, no alarms rang inside laboratories scattered across the planet. And yet, if you could rewind the universe to last night and compare it to this moment now, the two versions might not be perfectly identical. Not different enough to notice, not different enough to measure easily, just different enough to matter eventually. This is Whispers of the Universe. And if you are listening to this now, if you are curious about the quiet truths science rarely says out loud, take a moment to like this video, share it with someone who listens in the dark, and subscribe. Because tonight, we are questioning something most of physics has never been comfortable touching: the idea of constants. We are taught that the universe is built on numbers that do not move, that gravity pulls with the same strength it always has, that light always travels at the same ultimate speed, that the charge of an electron never hesitates, never drifts, never forgets what it is supposed to be. These numbers are called constants, not because they were proven eternal, but because everything we know collapses if they are not. They are the promises reality makes to itself. And yet, here is the uncomfortable thought. What if those promises are not carved into existence, but are instead being renewed, moment by moment, while we sleep? Imagine a clock so precise that it loses only 1 second over the lifetime of the universe. Now imagine a change even smaller than that. A shift so slow that no living mind could ever feel it. So gradual that every ruler, every clock, every detector changes along with it. If that were happening, how would we ever know? This question does not begin in speculation. It begins in silence. Because for over a century, physicists have noticed something peculiar. Whenever we measure the fundamental numbers of nature, no matter how carefully, we never get exactly the same result twice. The differences are tiny, infinitesimal, easily dismissed. They are filed away under a comforting name: error, measurement error, instrument error, environmental noise. And, most of the time, that explanation is correct. But not all errors behave like mistakes. Some errors repeat, some drift, some lean consistently in one direction across decades, and some refuse to disappear, no matter how advanced our instruments become. At first, this does not feel threatening. Science is built on approximation. No measurement is perfect. Reality is fuzzy at its edges. But what if the fuzziness is not coming from our tools? What if it is coming from reality itself? The idea feels wrong because it challenges something deeper than physics. It challenges our relationship with time. We assume that yesterday and today are connected by an unbroken sameness. That when we wake up, the rules governing the world have been waiting patiently for us to return. But that assumption is psychological before it is scientific. It comes from memory, and memory is a terrible measuring device. You do not remember every breath you took last night. You do not remember the exact rhythm of your heartbeat as you slept. And yet both were changing, moment to moment, without asking for your awareness. The universe may be doing the same thing, breathing, not metaphorically, numerically, a slow inhalation and exhalation of values we insist on calling fixed. The gravitational constant, for example. This single number determines how strongly every piece of matter pulls on every other piece of matter across the entire cosmos. It decides whether stars ignite or fail, whether galaxies hold together or dissolve, whether planets remain loyal to their suns. And yet, of all the constants in physics, gravity is the most stubbornly imprecise. Even today, laboratories around the world measure slightly different values for the same constant. They agree, but not perfectly, and they never have. For decades, this was brushed aside as experimental difficulty. Gravity is weak, hard to isolate, sensitive to interference. That explanation is reasonable, but reasonable explanations can still hide deeper truths, especially when no one is comfortable asking what happens if the explanation is incomplete. Because if gravity's strength were drifting even by a fraction of a fraction, then every orbit in the universe would be slowly rewriting itself. Not fast enough to panic, not fast enough to notice, just fast enough that 1 billion years from now, nothing would be where it once was. Then there is the speed of light. The ultimate speed limit. The backbone of space and time. According to everything we measure, light travels at the same speed in all directions, in all frames of reference. This is not just a property of light. It is a property of reality itself. Time stretches to protect it. Space bends to preserve it. And yet, there are theoretical models, serious ones, that allow this speed to have been different in the early universe. Slightly faster, slightly slower. Enough to solve mysteries we still struggle with today. If the speed of light could change then, what guarantees it cannot change now? The answer usually given is stability. The universe has settled. Its numbers have cooled. Everything has locked into place. But that answer is not a measurement. It is a hope. And hopes have a way of sounding like facts when repeated long enough. Consider the charge of the electron. Every electron in existence carries exactly the same charge. At least, that is what we say. If it did not, chemistry would fall apart. Atoms would not behave. Life would not exist. And yet, the precision with which we know this value has increased dramatically over time. Each new generation of instruments tightens the uncertainty, but it never reaches zero. There is always a margin, always a whisper of doubt. What if that margin is not shrinking because we are approaching perfection, but because the value itself is moving and our instruments are chasing it? Slowly, forever behind. This is where the question becomes uncomfortable, because if all the constants are changing together, coordinated, synchronized, then no experiment inside the universe could ever detect the motion. Your rulers would shrink with space. Your clocks would slow with time. Your detectors would drift with charge and mass. Everything would remain internally consistent. And consistency is what we mistake for truth. It would feel like stability. The same way sleeping feels like stillness. But sleep is not still. The body repairs itself. Neurons rewire. Hormones pulse. An entire internal universe shifts while consciousness is offline. When you wake up, you feel continuous, unbroken. But that continuity is an illusion created by memory stitching two states together. The universe may be doing something similar, resetting itself so gently that no seam is ever visible. If this is true, then today is not built on yesterday. It is built on a version of reality that has already drifted slightly away. And tomorrow will drift again, not toward chaos, not toward collapse, but toward a future that cannot be perfectly compared to the past. This idea unsettles physicists, not because it is dramatic, but because it is quiet. There is no explosion, no catastrophe, no moment of revelation, just an endless recalibration. A universe that never quite holds still long enough to be frozen into a formula. And perhaps that is why we cling so tightly to the word constant. Because it gives us the comfort of something not slipping through our fingers. But comfort has never been evidence. As you listen now, the planet is rotating beneath you. The galaxy is drifting through space. And the universe itself is expanding into something we cannot see the edges of. Change is already everywhere. The only difference here is scale, speed, patience. If the laws of physics are changing, they are doing so with extraordinary restraint. So restrained that even the most sensitive experiments only catch hints, anomalies, numbers that never quite settle. And maybe they are not meant to, because a universe that changed too quickly would tear itself apart. But a universe that changes slowly, that kind of universe gives life time to adapt, time to evolve, time to believe it understands what is happening. Tonight, we are not trying to prove that the constants are changing. We are doing something quieter. We are noticing that we have never truly proven they are not. And in that uncertainty, something begins to loosen. If reality can drift without us noticing, then certainty becomes temporary. Knowledge becomes provisional. And sleep, real sleep, becomes the perfect metaphor for existence itself. A state where immense activity hides behind stillness. As this thought settles, another question begins to form. If the universe can change without being detected, then how much of reality is shaped not by what is fixed, but by what moves together so perfectly that we never feel the motion? And if that is the case, what would be the first sign that something had finally fallen out of sync? Not tonight, not tomorrow, but slowly, quietly, over a span of time longer than memory. Let that question stay open, because the next step is not to look at the universe as a whole, but to examine the very idea of a constant and why the human mind needs them so badly in the first place. There is a reason the word constant feels comforting. It does not describe a number first. It describes a promise. When early physicists began to write equations for the universe, they quickly discovered something unsettling. The equations worked, but only if certain numbers were assumed to stay exactly the same forever. Not approximately, not on average, forever. These numbers were not derived from deeper laws. They were inserted, accepted, and once accepted, everything else made sense. Planets followed clean paths. Light obeyed strict limits. Matter behaved predictably enough to build machines, cities, civilizations. The universe appeared stable, and stability is intoxicating to a mind that evolved inside chaos. Because before constants, nature was not written in equations. It was experienced as weather, seasons, disasters, randomness. Fire burned sometimes. Floods came without warning. Stars were lights with no explanation. The introduction of constants did something profound. It turned the universe into something that could be trusted. A place where, if you measured carefully enough, the same input would always produce the same output. This was not just a scientific breakthrough. It was psychological relief. A declaration that beneath the surface noise of reality, there was a hidden layer that did not improvise. A layer that stayed loyal. And so, constants became sacred. Not officially, not ceremonially, but emotionally. They were treated as the immovable bones of existence. The gravitational constant, the speed of light, Planck's constant, the fine structure constant. Each one felt like a fixed pillar driven deep into the fabric of reality. Remove even one, and the structure collapses. Change it slightly, and stars fail to form. Atoms lose coherence. Chemistry forgets its rules. Life disappears. This led to a powerful, unspoken assumption. If life exists, then the constants must be fixed. Because if they were not, we would not be here to ask. At first glance, this feels logical, but logic has a way of hiding circular reasoning inside elegance. We assume constants are fixed because life requires them to be fixed, and we assume life exists because constants are fixed. The loop closes neatly, too neatly, because it quietly ignores a third possibility, that constants may be changing, but changing slowly enough that life can adapt alongside them. In biology, stability is rarely achieved by stillness. It is achieved by balance. Body temperature stays constant, not because it never changes, but because it is actively regulated. Ecosystems remain stable, not because species do not evolve, but because evolution happens continuously. Stability emerges from motion, not from freezing. Physics, however, prefers frozen things, frozen numbers, frozen assumptions, because moving targets are hard to measure. And yet, when physicists actually measure constants, what they find is not immobility. They find agreement within uncertainty. Every value is wrapped in a margin, a small plus or minus that says, this is where we believe the truth is hiding. The margins have shrunk dramatically over the last century. Our instruments are astonishingly precise. We can detect variations smaller than the width of an atomic nucleus, time intervals shorter than a billionth of a second. And still, the margins never vanish. There is always room for doubt. This is usually explained away as practical limitation. No tool is perfect. No environment is fully controlled. No measurement escapes noise. Again, this explanation is reasonable. But there is something subtle hiding beneath it. If constants were truly fixed, then as instruments improved, measurements should converge. The scatter should tighten around a single, immovable value. In many cases, this happens. But in some cases, convergence is strangely reluctant. Values cluster, then drift, then cluster again. Not wildly, not dramatically. Just enough to keep physicists cautious. Just enough to prevent absolute certainty. And this is where the human need for constants becomes visible. Instead of asking whether the numbers might be moving, we ask how to eliminate the error. Instead of questioning the assumption, we refine the method. Because questioning the assumption opens a door we are not ready to walk through. A door where the universe is not a static equation, but a slow process. A door where yesterday's laws are not identical to today's, only compatible. The discomfort here is not scientific. It is existential. If the rules of reality can change, even slightly, then permanence becomes a story we tell ourselves. A useful story. A productive story. But still, a story. The idea that something fundamental never changes gives us confidence to build upon it. We build technologies. We build theories. We build identities. Even our sense of self depends on constants. You believe you are the same person you were yesterday. Not exactly the same, but continuous enough to claim ownership of memory. This belief survives only because change happens slowly. If personality shifted abruptly, identity would fracture. The universe may rely on the same principle. Change that is too fast is destructive. Change that is slow becomes invisible. And invisibility masquerades as permanence. This is why the notion of drifting constants feels so unsettling. It suggests that the universe is not governed by eternal truths, but by evolving conditions. That reality is not a monument, but a process. And processes do not promise to stay where you left them. There is another reason physicists resist this idea: mathematics. The equations that describe nature are exquisitely sensitive. They balance delicately on the assumption that certain values do not move. Allow them to move, and the equations grow unstable. Predictability weakens. Control slips. Science becomes less about solving and more about tracking. And tracking something that moves slower than time itself is deeply frustrating. Because no single generation can confirm the motion. No single experiment can close the case. All that can be done is comparison. Across decades, across centuries, across civilizations. And comparison requires memory. Not human memory. Recorded memory. Data preserved with extreme care. Which introduces another complication. Our measurement systems are built from the same constants we are trying to measure. Our clocks rely on atomic transitions. Our rulers rely on electromagnetic interactions. Our detectors rely on particle properties. If those properties drift, our tools drift with them. The measuring stick stretches as the thing being measured stretches. The clock slows as time itself slows. Everything remains self-consistent, which is precisely what we observe. A universe that makes sense internally. A universe that never contradicts itself. And a universe that never confirms absolute stillness. This creates a strange asymmetry. We can detect abrupt changes easily. We are blind to synchronized ones. A planet suddenly changing orbit would alarm us. All planets slowly shifting together would feel like nothing at all. If constants are changing in isolation, physics would break. If they are changing together, physics would feel exactly the same. And this raises an uncomfortable question. Are constants truly constant? Or are they simply coordinated? The answer matters because it changes how we interpret everything that follows. If constants are fixed, the universe is a solved problem awaiting details. If constants evolve, the universe is an ongoing experiment. Not chaotic, not random, but unfinished. The need to believe in constants may not come from evidence, but from necessity. A universe with no anchors is hard to inhabit psychologically. So we name anchors into existence. We call them constants. We treat them as immovable. And we build entire frameworks around their presumed loyalty. But nature has never promised loyalty, only consistency. And consistency can arise from motion just as easily as from stillness. As this thought settles, something subtle happens. The question shifts. It is no longer, are constants changing? It becomes, how would we ever know if they were? Because if the universe is changing in its sleep, it is doing so without waking its inhabitants, without leaving fingerprints obvious enough to accuse it, which suggests that the next place to look is not at the numbers themselves, but at the places where measurements almost agree, yet never quite do. Those tiny disagreements we have trained ourselves to ignore, those persistent, gentle anomalies, the ones we call noise, the ones that refuse to go away. And if those whispers are not errors, then they are messages. Messages we have been hearing for a very long time, without realizing we were listening. And that leads us quietly toward the first suspect that science has learned to distrust too easily, the so-called measurement error. Because before we ask whether the universe is changing, we must ask whether error itself has been misunderstood. Gravity is the weakest force in the universe, and that is precisely why it is the most dangerous one to doubt. Compared to electromagnetism, gravity is almost nothing. Compared to the strong nuclear force, it is laughably fragile. And yet, gravity decides the architecture of everything large enough to matter. Without it, atoms could exist, but stars could not. Without it, particles could dance, but galaxies would never form. Without it, the universe would be a fog of isolated events, never collapsing into structure. Gravity is what turns time into history. At the center of gravity's rule sits a single number, a constant so quiet that most people never hear its name. The gravitational constant. It tells matter how strongly to pull on matter. Every planet obeys it. Every star trusts it. Every galaxy arranges itself around its value. And yet, this number has a secret. It is the least precisely known of all fundamental constants. This alone should feel strange. We can measure the charge of an electron to astonishing precision. We can measure the speed of light so well that it now defines our units of distance. We can measure atomic transitions with clocks that would lose less than a second over the age of the universe. But gravity resists this intimacy. No matter how carefully we try, gravity never quite gives us the same answer twice. Different laboratories, different continents, different decades. Each one reports a value that is close, very close, but never identical. At first, this does not alarm anyone. Gravity is difficult to isolate. It is weak. It is easily disturbed by nearby masses. The Earth itself interferes with every measurement. So the discrepancies are categorized: experimental challenges, systematic uncertainties, environmental noise. The explanations are not wrong, but something about gravity's stubbornness stands apart. Because unlike other constants, gravity does not converge cleanly as instruments improve. Instead, its measured value drifts, not wildly, not erratically, but persistently. Over time, the best estimate of the gravitational constant has shifted. Not by much, not enough to threaten physics, just enough to keep the number from settling into certainty. This is where the human mind intervenes. We assume the number is fixed, so we assume the measurements are flawed. The assumption comes first. Because if the number itself were drifting, the implications would be enormous. Gravity controls orbits. If gravity weakens, orbits expand. If gravity strengthens, orbits tighten. If this were happening rapidly, planets would betray the motion. But gravity, if it is changing, is doing so with extraordinary patience. So patient that every orbit adjusts smoothly. So patient that no sudden deviation ever appears. The Earth does not spiral into the Sunday. The Moon does not escape the Earth. The galaxies do not unravel. Everything looks calm. But calm is not evidence of stillness. In geology, continents move constantly. They collide, they separate, they reshape the planet. And yet, to a human lifespan, the ground feels unmoving. The planet seems fixed. Only when we zoom out over millions of years does the motion reveal itself. Gravity may be behaving in the same way. A force not frozen in place, but evolving on timescales that dwarf memory. If gravity's strength were decreasing extremely slowly, galaxies formed early in the universe would feel a slightly different pull than galaxies forming later. This could subtly influence how structures grow. If gravity were increasing, matter would clump more readily over time. Astronomers have noticed something curious. The large-scale structure of the universe does not behave exactly as simple models predict. Galaxies cluster in ways that require additional explanations. Dark matter, dark energy, invisible components introduced to preserve the assumption that gravity itself is constant. These ideas are powerful and mathematically elegant, but they share a hidden motivation. They allow gravity to remain unchanged. They protect the constant. What if that protection is unnecessary? What if gravity does not need invisible partners to explain the universe's behavior? What if gravity itself has been slowly shifting, quietly altering the cosmic balance? This idea is not new. Physicists have proposed theories where gravity evolves, not abruptly, not chaotically, but as a function of time or of the universe's expansion. In these models, gravity was stronger or weaker in the past. Such changes could explain discrepancies without invoking unseen substances. But there is a problem. Testing these ideas is nearly impossible. Because to test whether gravity has changed, we need a reference point that has not changed. And nothing qualifies. Our clocks depend on atomic processes. Our rulers depend on electromagnetic forces. Our detectors depend on particle interactions. If gravity changes alongside everything else, comparisons become meaningless. We are like passengers on a ship, measuring speed by watching the walls move. Everything moves together. So instead, we look for indirect evidence. Ancient light, fossil radiation from the early universe, patterns frozen into the cosmic background. These records suggest that gravity behaved very similarly billions of years ago. But very similarly is not the same as identically. There is room for motion, tiny room, but enough. And gravity's weakness makes this room larger, because small changes in a weak force take longer to accumulate into visible effects. Gravity is patient. It shapes the universe by whispering, not shouting. This patience makes it the perfect candidate for slow change. If gravity were to drift by a minuscule amount every million years, the effect over cosmic time would be profound. Yet within a human lifetime, nothing would seem wrong. The stars would still rise, the planets would still return, the equations would still work, until one day, far beyond us, they would not. And this possibility raises a subtle question. Why is gravity the weakest force at all? Physics has no satisfying answer. It simply is. Some theories suggest gravity's weakness is a consequence of extra dimensions. Others suggest it is diluted across scales we cannot access. But another possibility is rarely discussed. Gravity may be weak because it is changing. A force in transition cannot dominate. A force in motion cannot lock reality into rigidity. This idea is uncomfortable because it reframes stability. Stability becomes a temporary alignment, not a permanent condition. The universe appears balanced not because nothing is moving, but because everything is moving together. And gravity, as the architect of large-scale order, may be adjusting its grip continuously to maintain that balance. This is not purposeful, not intelligent, just mechanical, like a thermostat that never stops correcting. But correction implies deviation, and deviation implies motion. Here is where gravity's story intersects with sleep. When you sleep, your body does not shut down, it recalibrates. Blood pressure shifts, neural connections are strengthened or pruned, hormonal balances are adjusted. You wake up feeling continuous, but internally, you are not the same system you were before. The difference is subtle, but real. Gravity may be doing the same thing, recalibrating the universe so slowly that no single moment reveals the adjustment. Only long arcs tell the story. And even then, the story is ambiguous. Because we do not observe gravity directly, we observe its effects. And effects can be explained in multiple ways. We can always add another component, another field, another invisible influence, as long as gravity itself remains untouchable. This is why the gravitational constant is such a revealing case. It exposes the tension between what we assume and what we can actually verify. We assume gravity's strength is fixed, but we cannot prove it with the certainty we assign to it. We live inside gravity's domain. We cannot step outside it to check. So we trust consistency. But consistency can arise from coordination. If gravity changes in sync with the expansion of space, with the flow of time, with the properties of matter, then nothing locally appears wrong. Everything fits, until we compare vastly separated eras. And even then, interpretation remains open. This makes gravity less like a law and more like a habit, a behavior that is held long enough to feel permanent. But habits can change, slowly, so slowly that those living inside them mistake motion for rest. If gravity is drifting, it is doing so with extraordinary discretion. Which brings us back to the problem raised at the end of the last chapter. How do we tell the difference between error and evolution? Between a flawed measurement and a moving target? Because gravity's ambiguity is not unique. It is simply the most familiar, the most forgiving, the force that teaches us that weakness can hide change better than strength ever could. And if gravity has taught physics to tolerate uncertainty, then perhaps the next place to look is not at forces that bind stars, but at the errors we dismiss without listening. Because before we can accuse gravity of drifting, we must confront the concept that has been shielding constants from suspicion all along. The idea that disagreement means mistake. The idea that error is always human and never fundamental, which leads us, quietly and inevitably, toward the question science avoids asking too directly. What if error itself is the signal? What if the universe has been speaking through imperfection, and we have been correcting it into silence? Light does not feel negotiable. Of all the numbers in physics, this one carries the most authority. It is not just a speed, it is a boundary. Nothing outruns it. Nothing bypasses it. Time itself bends to make sure it is never violated. When physicists speak of the speed of light, they speak with a confidence that borders on reverence. Because this number does not merely describe how fast light moves. It defines how space and time are stitched together. Change it, and clocks behave differently. Change it, and distances collapse or stretch. Change it, and causality itself begins to wobble. This is why the speed of light feels untouchable. Not because it has been proven eternal, but because too much depends on it remaining exactly as it is. Yet, here is the first quiet fracture in that certainty. We do not measure the speed of light the way we imagine. We do not watch a beam leave a source and chase it across the universe. Instead, we define it. In modern physics, the speed of light is no longer something discovered. It is something declared. 1 meter is defined as the distance light travels in a specific fraction of a second, which means the speed of light is exact by definition, perfect, unquestionable, and yet this perfection is circular. We measure distance using time. We measure time using atomic processes, and those atomic processes are governed by the same physical laws we assume to be fixed. The measurement system closes in on itself. It becomes internally flawless, but internal flawlessness does not guarantee external immobility. Before the speed of light was defined, it was measured, and those measurements tell a subtler story. Early experiments struggled to pin it down. Different methods produced slightly different results. Over time, the value seemed to creep upward as instruments improved. This is usually explained as refinement, better tools, better corrections, better understanding, and again, that explanation is reasonable. But notice the pattern. Whenever a constant appears to drift, the drift is always explained as error being removed, never as motion being revealed. Because motion would imply something uncomfortable. It would imply that the universe once behaved differently. In fact, there are serious cosmological models that suggest exactly that. In the earliest moments after the universe began, the speed of light may not have been what it is now. Some theories propose it was higher, not infinitely higher, just enough to allow distant regions of the universe to communicate before settling into the slower pace we observe today. These models were not invented casually. They were introduced to solve real problems. Why is the universe so uniform in temperature across vast distances? Why do distant regions appear coordinated without time to interact? A faster early speed of light would help. And if it could change then, why are we so confident it cannot change now? The usual answer is stability. The universe cooled. Its parameters froze. The chaos ended. But freezing is an assumption, not a measurement. It is a narrative that feels satisfying. Yet when we look closely, what we see is not freezing. We see equilibrium. And equilibrium is dynamic. A spinning top remains upright not because it is motionless, but because opposing forces are balanced. A living organism maintains homeostasis not because nothing changes, but because change is continuously corrected. The speed of light may be part of such a balance, a negotiated limit, maintained, not guaranteed. There is another detail that complicates the picture. We never measure the one-way speed of light directly. Every measurement relies on light traveling out and coming back, a round trip. To measure the one-way speed, we would need 2 perfectly synchronized clocks at different locations. But synchronization itself depends on light signals, which means the method assumes what it tries to test. This is not a flaw in physics. It is a fundamental limitation, and within that limitation, subtle possibilities hide. If the speed of light were drifting uniformly everywhere, our synchronization procedures would drift with it. No contradiction would arise. Everything would remain consistent. We would live inside a bubble of agreement. This brings us back to a recurring theme. Consistency does not imply immobility. It implies coordination. If all clocks slow together, time feels normal. If all rulers stretch together, distance feels unchanged. If the speed of light shifts alongside the structure of space-time, nothing locally breaks. The universe remains polite, predictable, calm. This politeness is deceptive because it allows slow change to masquerade as permanence. Light's authority comes not from proof, but from necessity. It is the keystone of relativity. Remove it, and the arch collapses. So physics protects it. The way civilizations protect myths that hold them together, not with lies, but with selective attention, by asking questions that can be answered within the framework and quietly avoiding those that cannot. This does not mean physicists are dishonest. It means they are human. They work inside structures that reward coherence, and coherence depends on constance behaving. But nature is not obligated to preserve our frameworks. It only needs to preserve its own continuity. And continuity does not require stasis. It requires smoothness. Light, if it is changing, would change with extraordinary smoothness. No jumps, no shocks, just a gradual recalibration that every process follows. The universe would not feel faster or slower. It would simply feel like itself. There is a deeper implication here. If the speed of light defines causality, and if it can drift, then the boundary between cause and effect is not absolute. It is contextual, dependent on era, dependent on scale. The universe you live in may obey slightly different causal constraints than the universe billions of years ago. Not different enough to feel alien, just different enough to shape history. This does not violate science. It extends it, but extension requires patience, because such changes cannot be proven in a single experiment. They reveal themselves only through patterns, through mismatches between expectation and observation, through anomalies that refuse to align perfectly. The cosmic microwave background carries hints of an early universe that does not quite match simple assumptions. Large-scale structures hint at coordination beyond naive limits. Each hint can be explained individually, but together they form a question. What if light speed is not a rigid ceiling, but a negotiated speed limit that evolves as the universe expands? What if the universe adjusts its own communication speed to remain coherent? This would mean the universe is not a static object, but a system managing itself, not intelligently, not consciously, but mechanically, like a river adjusting its flow around obstacles. And if light is part of that adjustment, then time itself is not marching forward at a fixed pace. It is being metered, released in controlled increments. This idea is unsettling because it dissolves absolutes. But absolutes have always been a convenience. They allow us to stop asking certain questions. They give us ground to stand on. If the speed of light is absolute, we can build confidently. If it is negotiable, even slightly, then reality is less like a monument and more like a process. Processes do not end. They only drift. As you listen, photons are entering your eyes. They have traveled vast distances. They have obeyed the same speed they always do. At least, that is how it feels. But feeling is not measurement. And measurement, in this case, cannot escape circularity, which leaves us with a quiet uncertainty. Light may not be lying to us, but it may be speaking in a language where change is hidden by symmetry. If that is true, then light is not the exception among constants. It is the pattern, a reminder that the most trusted numbers in physics are trusted because they behave too politely to betray their motion. And this realization pulls our attention towards something even smaller, even quieter, something that operates at the scale of atoms, at the scale where our clocks tick, where our rulers are defined, where our very notion of precision begins. Because if change is hiding anywhere, it is hiding where we believe measurement is safest, inside the smallest charges, the tiniest masses, the numbers we think we know best. which means the next place to look is not outward, towards stars and light years, but inward, toward the electron, and the charge it carries without ever seeming to hesitate. If gravity governs the large, and light governs the limit, then the electron governs intimacy. It decides how atoms hold together, how molecules form, how chemistry becomes biology. Everything you are made of depends on one impossibly small value: the electric charge of the electron. It is the same everywhere, or at least, that is what we say. Every electron ever measured carries exactly the same charge. Not approximately, exactly. This belief is so deeply embedded that most physics textbooks do not even pause to justify it. They state it and move on, because if electrons did not agree on this value, nothing stable could exist. Atoms would fail to assemble. Molecules would refuse to cooperate. Life would never emerge. The universe would be a cloud of unfinished interactions. So the charge of the electron becomes sacred, not because it has been proven eternal, but because questioning it feels dangerous. Yet, once again, the certainty dissolves when we look closely. We do not measure the charge of an electron directly. We infer it from how electrons move in electric fields, from how atoms emit light, from how currents behave in carefully controlled environments. Each method agrees, but agreement is not identity. There is always uncertainty, always a margin so small it feels irrelevant. A few parts per billion, a few parts per trillion, numbers so tiny they vanish into abstraction. And yet, everything depends on them. What makes the electron's charge particularly interesting is not the size of the uncertainty. It is the structure of the agreement. Measurements cluster. They align, but they do not collapse into a single, perfect value. Instead, they form a narrow band, a range, and that range persists. As instruments improve, the band narrows, but it never disappears. This is expected. No experiment is flawless. But the persistence of the band raises a quiet question. What if the electron's charge is not a point, but a moving window? What if the value is drifting so slowly that every generation of instruments merely captures a snapshot, each snapshot sharp, each snapshot precise, but none definitive? Because definitiveness would require stillness, and stillness is an assumption. The electron is not an object in the classical sense. It is a manifestation of a field, a ripple in something deeper. And fields, by their nature, are dynamic. They fluctuate, they interact, they respond. If the underlying field that gives rise to electric charge were evolving very slowly, then the charge of the electron would evolve with it. Not abruptly, not detectably, but enough to matter over deep time. This possibility is rarely discussed because it disrupts a foundational comfort. Electric charge is woven into nearly every measurement we make. Our clocks depend on atomic transitions. Those transitions depend on electromagnetic interactions. Those interactions depend on the electron's charge. If that charge were changing, our clocks would change too. Time itself would drift alongside the value we use to measure it, which means time would never feel wrong. It would feel continuous, natural. This is the recurring trap. Whenever a constant governs both the system and the measuring device, motion becomes invisible. The yardstick stretches with the distance. The clock slows with the process. Everything remains consistent. And consistency feels like proof, but it is not. It is merely coherence. The fine structure constant brings this issue into sharper focus. It is a dimensionless number, a ratio, not tied to units of length or time. It describes the strength of electromagnetic interaction itself, how strongly light and matter talk to each other. If there were ever a place to catch change, this would be it. Because dimensionless constants are harder to disguise. They are comparisons, not measurements. And yet, even here, the evidence whispers rather than shouts. Some observations of distant quasars' light that has traveled billions of years suggest that the fine structure constant may have been slightly different in the deep past. Not conclusively, not universally, but intriguingly, enough to generate debate, enough to resist dismissal. These observations are controversial. They push instruments to their limits. They rely on subtle, spectral shifts, and so they are treated cautiously. But caution cuts both ways. If the data suggested no change, we would be satisfied. But when the data hints at change, we demand extraordinary certainty. Because change threatens structure. The electron's charge feels like the last place change should hide. It governs the smallest scales, the scales we believe we understand best, but history suggests the opposite. It is often in the smallest assumptions that the deepest revisions occur. Classical physics assumed continuity until quantum discreteness shattered it. Newtonian time assumed universality until relativity fractured it. Each time, the constants survived, but their meanings shifted. Perhaps the electron's charge is not a fixed token stamped onto reality. Perhaps it is a relationship that evolves as the universe evolves. A balance struck between fields that are themselves changing. If that is true, then chemistry in the early universe was subtly different. Reaction rates, bond strengths, energy levels, all shifted slightly. Not enough to erase atoms, just enough to bias outcomes. And bias, over billions of years, becomes structure. The universe we see may be the result of such biases accumulating, not from constants being perfect, but from them being patient. The most unsettling aspect of this idea is how ordinary it feels. There is no drama, no cosmic warning, just slow drift. So slow that even the concept of change begins to feel misplaced. Is something changing if it never breaks continuity? Is motion real if it has no fixed reference? The electron does not announce itself. It behaves, reliably, predictably, and that predictability seduces us into assuming permanence. But predictability only requires short-term consistency. It does not require eternal fixity. Your heartbeat is predictable, yet it is never the same beat twice. Your breathing follows a pattern, yet no two breaths are identical. Life itself thrives on controlled variation. Why should the universe be different? If the electron's charge is drifting, it is doing so in harmony with everything else. And that harmony is precisely why we do not hear it. Because noise stands out, harmony blends in. The universe may not be hiding change. It may simply be changing musically. Every value adjusting just enough to keep the melody intact. Which leads us deeper into the problem of detection. If even dimensionless ratios can drift quietly, then what hope do we have of anchoring reality? Where do we place the pin that does not move? The answer may be uncomfortable. We may not get one. We may be living inside a system where all reference points are internal, where comparison replaces absolutes, where constants are not commandments, but agreements, agreements that have held long enough to feel eternal. And if that is the case, then the story of changing constants is not about instability. It is about coordination. A universe that refuses to tear itself apart by allowing anything to change alone. Which brings us to the next step. If constants are coordinated, then their changes must be linked. And if they are linked, there must be a mechanism, something deeper than individual forces, something that orchestrates the drift. To look for that, we must step back from individual constants and ask whether time itself is part of the disguise. Because if time stretches and contracts alongside everything else, then change becomes not just hidden, but structurally unobservable. And that thought pulls us toward a more unsettling question. Is time watching the universe change? Or is time changing with it? Every number in physics carries a shadow, a small symbol placed beside it, a quiet admission, plus or minus. This symbol is so familiar that we stop seeing it. We glance past it, we ignore it. Because the number is what feels real. The uncertainty feels like a footnote, but the universe may be hiding inside that footnote. From the beginning of measurement, error has been treated as a human problem, a limitation of tools, a weakness of technique, a failure of control, never as a feature of reality itself. When two experiments disagree, we do not ask whether nature has changed. We ask which experiment was wrong. This instinct is not irrational, it is necessary. Without it, science would dissolve into ambiguity. But necessity does not equal truth. And sometimes, the habits that make science powerful also make it blind. Measurement error is assumed to be random. Noise, something that averages out if you collect enough data. If you repeat the experiment enough times, the true value will reveal itself. This belief underpins modern physics, and in many cases, it works beautifully. But there is a category of error that behaves differently. Errors that are not random, errors that persist, errors that cluster, errors that refuse to be averaged away. These are usually labeled systematic errors, hidden biases in instruments, environmental influences not fully accounted for, unknown variables. Again, this explanation is often correct. But notice what never enters the conversation: the possibility that the value itself is not fixed, because once that possibility is allowed, error stops being a nuisance. It becomes a signal, and signals are dangerous. They demand interpretation. They demand humility. Consider how error behaves across time. Measurements taken decades apart often disagree slightly. Not wildly, not chaotically, but directionally. Values creep, not enough to alarm, just enough to require updated, best estimates. Physics textbooks quietly revise numbers. No announcement, no explanation, just refinement. Progress. But what if refinement is indistinguishable from pursuit? What if the value is moving, and measurement is following it? Always behind, always catching up to a past state, never quite arriving. This would produce exactly what we see: a narrowing uncertainty band that never collapses, a consensus that shifts slightly as instruments improve, a sense of convergence without finality. The assumption that error is human protects us from this interpretation, because if error is always human, then reality remains pristine, unmoving, reliable. But what if reality is not obligated to be pristine? What if it is only obligated to be coherent? There is a subtle asymmetry in how we treat error. When theory and experiment disagree, we blame the experiment. When two experiments disagree, we blame the newer one. When old data conflicts with new data, we call it outdated. The direction of trust always flows toward the present, toward improved instruments, toward refinement. But this assumes the target is stationary. We never ask whether the target itself might be drifting forward in time, because drift is not part of the measurement framework. To allow drift would require a reference outside time, and we do not have one. All measurements are made inside the universe, inside its processes, inside its clocks. If those processes are changing, then measurement becomes a moving conversation, not a snapshot. This is not how physics likes to think. Physics prefers timeless truths, equations that hold regardless of era, laws that do not age. But aging may be unavoidable, not because laws decay, but because the conditions under which they operate evolve. Error, in this context, becomes a kind of camouflage. It absorbs deviations. It smooths over discrepancies. It reassures us that nothing fundamental is wrong, as long as the deviations remain within the expected margin. But who decides what margin is expected? Margins are set by us, by confidence, by convention, by what feels reasonable, and reasonableness is shaped by belief. Belief in stability. There is a telling pattern in the history of physics. Whenever a discrepancy grows too large to ignore, two responses are possible. Either we introduce a new entity to preserve existing laws, or we revise the laws themselves. Dark matter preserves gravity. Dark energy preserves cosmic expansion models. Inflation preserves uniformity. Each addition saves constants from accusation. Each addition keeps the numbers clean, and each addition pushes uncertainty elsewhere. This strategy works remarkably well, until it doesn't, because adding unseen components increases complexity, and complexity eventually demands justification. At some point, the question arises: are we explaining the universe, or are we protecting our assumptions? Error is a convenient buffer. It allows us to delay that question indefinitely. As long as discrepancies are small, they can be absorbed. As long as they are framed as noise, they can be ignored. But what if the universe is not noisy? What if it is precise, but evolving? Then the deviations we see are not mistakes. They are timestamps, markers of slow motion. But slow motion requires patience to detect. It requires comparison across eras, across civilizations, across technological thresholds. And that kind of comparison is rare, because science advances quickly. Each generation discards the previous one's tools. Old data becomes less trusted. less relevant, less precise. But old data is the only window we have into the past behavior of constants. If we always privilege the newest measurement, we erase the trail. We smooth history into the present. And in doing so, we erase evidence of drift. This creates a paradox. The better our instruments become, the harder it is to notice slow change. Because improved precision narrows focus, it reduces tolerance, it encourages certainty, and certainty discourages comparison. Why look back when you believe you see clearly now? But clarity can be deceptive. A microscope shows detail, not context. A telescope shows distance, not duration. To detect drift, we need time more than precision. We need memory more than resolution. And science is not built to preserve memory. It is built to replace it. This is why the idea of changing constants feels so elusive. It slips through the cracks of methodology. It is too slow for experiments, too subtle for intuition, too threatening for assumption. Error becomes the perfect hiding place. It is where anomalies go to disappear. But not all anomalies disappear. Some return, again and again, reappearing in different contexts, in different constants, in different eras, always small, always ignorable, always just within tolerance. These recurring discrepancies form a pattern that does not scream. It whispers, and whispers are easy to dismiss, especially in a discipline trained to listen for loud signals, explosions, spikes, breakdowns. The universe, if it is changing its constants, is doing so politely. It is not interrupting. It is not demanding attention. It is adjusting itself while the observer is distracted. Much like sleep. When you sleep, your body changes more than when you are awake. Cells repair damage. Memories are reorganized. Connections are pruned and strengthened. But consciousness experiences sleep as absence, as nothing happening. Only when you wake do you feel subtly altered, rested, different, but unable to point to a moment when the change occurred. The universe may be changing in exactly this way, its deepest parameters adjusting during spans we cannot perceive. Error, then, is not a flaw. It is a side effect of observation within a changing system. The plus or minus symbol may not represent ignorance alone. It may represent motion, a range because the value itself occupies a range over time. This does not mean science is wrong. It means science is incomplete. It has not yet learned how to think temporally about constants. It treats them as static truths rather than evolving relationships. And relationships evolve quietly, especially when all participants evolve together. Which brings us to a deeper problem. If error is the signal, how do we separate it from noise? How do we tell drift from defect? We cannot simply accept every discrepancy as evidence of change. That way lies chaos. But we also cannot dismiss every discrepancy without question. That way lies stagnation. The answer, if it exists, lies not in individual measurements, but in correlations, patterns across constants, synchronized deviations, small shifts that echo in multiple domains. If gravity, light, charge, and time all show anomalies that align, then error stops being isolated. It becomes collective. And collective error is no longer error. It is behavior, which means the next step is not to examine constants one by one, but to ask whether their uncertainties move together, whether their deviations rhyme, whether there is a deeper layer beneath them all, a layer that governs not values, but change itself. And to reach that layer, we must confront the most uncomfortable possibility yet. That time, the very medium in which change is measured may not be the neutral backdrop we imagine. Because if time itself is drifting, then error is not hiding change. It is announcing it, softly, persistently, waiting for us to listen. There is a quiet rule in science. If an experiment is done carefully enough and repeated often enough, the results should converge, not immediately, not perfectly, but eventually. This belief is so foundational that it rarely gets questioned. It is the promise that repetition will reveal truth. Run the experiment again, refine the setup, reduce interference. Truth will emerge. And for much of physics, this promise holds. Drop an object, measure acceleration. Repeat. The numbers settle. But there is a category of experiments where convergence behaves strangely. They converge, and then hesitate. They approach agreement, but never collapse into identity. Instead of a single value, we get a narrow band. Instead of certainty, we get confidence with conditions. This happens often enough that it feels normal. So normal that we stop asking why. We call it experimental reality. But look closer. Across different laboratories, using different methods, on different continents, the same constants are measured. The results agree within uncertainty, but they are not the same. They are never exactly the same. And more importantly, the differences are not random. They do not scatter evenly around a central value. They cluster, they drift, they show preference. One lab consistently measures slightly higher, another slightly lower. Over years, the best value shifts, not dramatically, just enough to update the tables. This behavior is usually explained away with calm professionalism. Hidden biases, subtle environmental effects, unaccounted variables. Again, none of this is unreasonable. But there is a deeper question hiding underneath. Why do these disagreements persist, even as methods diversify? If one method were flawed, another should correct it. If one environment were biased, another should cancel it out. And yet, across decades, the disagreement survives. What if the disagreement is not about method, but about time? Every experiment is performed at a moment embedded in a larger process. If the value being measured is drifting even slightly, then experiments separated by years are not measuring the same thing. They are measuring neighboring states, close enough to agree, different enough to disagree. This would create exactly what we see: a history of precision without finality, a tightening spiral that never reaches the center. Physics does not like spirals. It likes endpoints. It likes answers that stop moving. But the universe may not share this preference. There is a telling asymmetry in how data is treated. We rarely compare experiments separated by decades directly. Instead, we recalibrate. We normalize. We correct old data to match new standards. In doing so, we erase temporal context. We compress history into the present. This is efficient, but it also removes the one dimension where drift could reveal itself: time. Imagine trying to detect continental drift by constantly redefining the map so that continents always appear aligned. You would never notice movement. Everything would look stable. This is essentially what modern precision science does. It aligns results to current standards. It enforces consistency. It rewards agreement, which means it quietly penalizes temporal deviation. The better science becomes, the harder it is to notice slow change. This is the paradox. Precision blinds us to motion that unfolds beneath it. This is why repeated experiments are such a fascinating test case. They are meant to remove uncertainty, but they may be doing the opposite. They may be smoothing over evidence, because repetition assumes stationarity. It assumes the target is not moving. If that assumption fails, repetition does not reveal truth. It averages it away. There is an analogy here with sound. If a tone slowly changes pitch over hours, you will not hear it as movement. You will hear it as a steady note. Only when you compare recordings far apart in time does the shift become audible. The universe may be playing a note like this, a constant tone that is imperceptibly sliding. Each experiment hears a pure sound, but no single listener hears the slide, because the slide is too slow. The consequences of this are profound. It means that agreement between experiments does not necessarily confirm constancy. It only confirms synchronization. All experiments are synchronized to their era, to the same underlying state of the universe, which means they agree with each other, but not necessarily with the past. This is why ancient measurements matter so much, not because they were precise, but because they were anchored to a different moment. Even crude data can reveal trends if the timescale is long enough. But modern science distrusts crude data. It prefers precision, so it discards history, or corrects it beyond recognition. This is not negligence. It is optimization. But optimization has side effects. One of them is amnesia, and amnesia is the perfect condition for undetected drift. This brings us to a subtle realization. The idea that all experiments agree may be misleading. They agree with each other now, They agree within a narrow slice of time. But agreement across time is rarely tested. And when it is, discrepancies are framed as progress, not change. We improved the method. We refined the value. We got closer to the truth. But what if truth is not a point? What if it is a trajectory? Then refinement is not convergence. It is pursuit, and pursuit never ends. This reframing changes how we interpret decades of careful work. It does not invalidate it. It contextualizes it. Every experiment becomes a snapshot of a moving landscape. Each result precise, honest, correct, and yet incomplete, because it is missing the dimension of motion. This is why the notion of changing constants feels both radical and strangely mundane. Nothing dramatic happens. Science continues to function. Predictions remain accurate. Technology works because the change is slow. Slow enough that engineering tolerances absorb it. Slow enough that biological systems adapt unconsciously. Slow enough that identity remains intact. You do not feel older from one second to the next, but you are changing constantly. Your cells replace themselves. Your neural patterns shift. Your internal chemistry drifts. Stability emerges from turnover. The universe may operate on the same principle, and repeated experiments may be witnessing this turnover without recognizing it. Each result correct. Each result faithful. Each result measuring a universe that is no longer exactly the same as the one before. This raises an uncomfortable possibility. What if science's greatest strength, its insistence on reproducibility, is also its blind spot? What if reproducibility confirms coherence, not immobility? What if the universe is reproducible because it is well coordinated, not because it is frozen? If that is the case, then the lack of exact agreement between experiments is not a failure. It is a signature, a sign that something is moving beneath the surface. But to see that motion, we must stop treating disagreement as embarrassment. We must stop apologizing for imperfection. We must begin to read the gaps, because gaps are where motion hides. And if we learn to read them, they may point us toward a deeper layer of reality, a layer where constants are not eternal numbers, but parameters being continuously adjusted in relation to something larger, something that governs not values, but the evolution of values, which brings us closer to the question we have been circling without naming. If constants change together, what is coordinating them? And to answer that, we must finally confront the idea that has been silently shaping every measurement we make. The idea that time itself is neutral, a passive stage, a silent witness. Because if time is not neutral, then nothing we have discussed so far can be understood in isolation. And that is where the next drift begins. There is a kind of change that no instrument is designed to detect. Not because it is too fast, not because it is too chaotic, but because it is too gentle, too continuous, too well behaved. Imagine watching the hour hand of a clock. If you stare at it, it never moves. Not really. And yet, after some time has passed, it is undeniably elsewhere. The movement was real, but perception never caught it in the act. This is the kind of change that challenges measurement, not by breaking rules, but by obeying them too perfectly. The hypothesis that the universe might be changing its constants slowly does not propose instability. It proposes drift, a drift so gradual that every process within the universe adjusts along with it. A drift that never creates discontinuity, never produces a moment of contradiction, never triggers an alarm. If such a drift exists, it would not feel like change. It would feel like continuity. This is why the idea has been so hard to formalize. Physics is excellent at detecting deviations, spikes, anomalies, breakdowns, but it is poorly equipped to detect synchronized evolution. When everything changes together, comparison collapses. There is no fixed reference. Every measuring device becomes part of the phenomenon. This is not speculation. It is a known limitation. All clocks are physical systems. All rulers are physical systems. All detectors are governed by the same constants they attempt to measure. If those constants evolve, the tools evolve too, not as errors, as participants. This is where the notion of slow drift becomes unsettling. because it suggests that reality may be changing in a way that is fundamentally unobservable from within, not hidden. Unobservable by design, the universe may be transparent to itself. This idea first appears absurd. Science is built on the assumption that reality is observable, that given enough ingenuity, enough patience, enough precision, truth will reveal itself. But this assumption quietly depends on one thing: that the thing being observed is not evolving in lockstep with the observer. If it is, then observation becomes relational, not absolute. You can still predict, you can still calculate, you can still build, but you cannot anchor, and anchoring is what we mistake for knowing. The slow drift hypothesis does not claim that constants wander freely. It suggests they are constrained, coupled, linked to the expansion of the universe, linked to the distribution of energy, linked to the passage of time itself. In such a model, constants are not arbitrary numbers. They are state variables. They describe the current condition of the universe, not an eternal rulebook. This reframes the idea of law. A law becomes a pattern that holds for now, reliable, stable, but not immortal, and immortality was never promised. Consider how temperature works. At any given moment, a system has a temperature. That temperature can remain constant for long periods, but it is not a fundamental property of existence. It emerges from motion, from averages, from equilibrium. If the universe has something like a cosmic temperature that influences its constants, then slow drift becomes natural. As the universe expands and cools, those parameters adjust, not abruptly, smoothly. This is not radical thinking. Early cosmology already accepts that conditions were different in the past. Particles behave differently. Forces were unified. Symmetries were broken as the universe cooled. What is radical is the assumption that this process stopped completely. That evolution gave way to stasis, that the universe reached a final configuration and froze its deepest parameters. There is no direct evidence for that freeze. There is only convenience. The equations are easier when things stop changing, but ease is not evidence. The slow drift hypothesis suggests continuity instead of cessation. No sudden transitions, no final settling, just an ever-slowing evolution. Like a pendulum that never quite stops swinging. Its motion becomes imperceptible, but it does not vanish. This would explain something subtle: why the universe feels so finely tuned, why constants appear balanced on a knife's edge, why small changes would destroy complexity. Because they are not free to change independently. They move together, coordinated, constrained by deeper relationships. The tuning is not a miracle, it is maintenance. This is a difficult idea to accept because it removes the sense of finality. It suggests the universe is not done, not complete, not locked in. It is still becoming. But becoming does not mean chaotic. It means conditional. Everything that exists does so because conditions are right. And conditions can drift without collapsing structure. Life itself is proof of this. The chemical environment of Earth has changed dramatically over billions of years. Atmospheric composition shifted. Temperatures varied. Radiation levels fluctuated. Life did not require stasis. It required continuity, the ability to adapt alongside change. If life can survive slow environmental drift, why could the universe not survive slow parametric drift? In fact, slow drift may be the reason survival is possible. A universe that never changes may be brittle. A universe that changes slowly can correct itself. This introduces a new way of thinking about cosmic stability. Stability does not come from rigidity. It comes from responsiveness. The universe remains intelligible because its changes are smooth. Equations continue to work because the parameters evolve gently. Predictions remain accurate because the drift is slower than observation. This also explains why there is no obvious moment of discovery. No experiment that shouts, "The constants are changing," because discovery requires contrast, and contrast requires a fixed backdrop. The slow drift universe offers no backdrop, only flow. This brings us back to the role of memory. Human memory is not continuous. It samples, it stitches, it fills gaps. We remember ourselves as stable because change happens between recollections. The universe may operate on the same principle. It remains stable because its changes occur between measurements, between generations, between civilizations. When we compare now to then, we smooth over the difference. We attribute it to error, to progress, to refinement, because our narrative expects improvement, not drift. We believe we are approaching truth, not chasing it. The slow drift hypothesis suggests something humbler. We are tracking truth as it moves, never catching it, always close enough to function. This does not make science futile. It makes it contextual. Science becomes a map, not a monument. A map that updates slowly, so slowly that we mistake updates for corrections. There is a psychological reason this idea feels unsettling. It removes absolutes, and absolutes are comforting. They give us something to lean on, something that does not ask to be reevaluated. If constants can change, even imperceptibly, then nothing is immune to revision. Not even the foundations. But perhaps that is not a flaw. Perhaps it is a safeguard. A universe with no capacity for internal adjustment would fracture under stress. A universe with gentle drift can absorb change. It can rebalance. It can remain habitable. This shifts the emotional tone of the idea. The universe changing its constants while we sleep is not an act of betrayal. It is an act of care, not intentional care, mechanical care, like a system that constantly retunes itself to remain coherent. But coherence has a price. It hides motion. It conceals evolution behind smoothness. And smoothness feels like permanence, which is why this hypothesis has remained on the edge of discussion. It is not falsified. It is not confirmed. It simply does not fit the way we like to think. Because to accept it, we must accept that certainty is temporary. That knowledge has an expiration date. That the universe is not a solved puzzle. It is an ongoing process. And processes do not end. They only slow. As this idea settles, a new question quietly emerges. If the universe is drifting in this coordinated way, then what is it drifting with respect to? What sets the pace? What defines the direction? Because drift is not random. It has structure, and structure implies a deeper parameter, a hidden clock, not a clock we can read, but a clock that everything obeys. To find that clock, we must stop looking at space, stop looking at constants, and finally look at the thing that has been silently assumed to be neutral from the beginning, time itself. Because if time is not fixed, then drift is not a side effect. It is the mechanism, and that is where the next layer begins to open. There is a quiet assumption hiding beneath every measurement, that time is neutral, that it flows forward at a steady pace, independent of what it carries. We treat time like a conveyor belt. Things move on it, change happens on it, but the belt itself is assumed to be rigid, unchanging, reliable. This assumption feels so natural that questioning it sounds absurd. And yet, nothing in physics truly supports it. Time is not an external backdrop. It is part of the system, intertwined with space, influenced by energy, bent by gravity. It slows near massive objects. It stretches at high speeds. It ages differently depending on where you stand. This alone should make us suspicious of its neutrality. If time can dilate, contract, and warp, then its role is not passive. It participates, which raises a subtle but unsettling question. If the constants of physics are drifting, is time merely witnessing that drift, or is time drifting with them? To ask this properly, we must first ask something simpler. If today is not exactly the same as yesterday, what would notice first? Not humans. Human perception is too coarse. Our senses integrate over moments. Our memories blur detail. We notice change only when it crosses thresholds. Time itself might be changing continuously, and we would never feel it. The first to notice would not be consciousness. It would be systems that accumulate error, clocks. But clocks are not ideal observers. They are built from atoms. Atoms depend on electromagnetic interactions. Those interactions depend on constants. If constants drift, clocks drift. A clock cannot detect its own deformation. It will tick confidently, faithfully, incorrectly, without ever knowing. So we look to comparisons. Atomic clocks against astronomical clocks, planetary motion against atomic transitions, orbital periods against decay rates. These comparisons are extraordinarily precise, and they agree. But again, agreement does not imply immobility. It implies synchronization. All these systems are embedded in the same temporal fabric. If time itself is changing, they change together. The conveyor belt stretches, but everything riding it stretches too. Nothing falls off, nothing slips, which means no alarm sounds. This is why the idea of a drifting present is so difficult to grasp. We experience time relationally. We measure durations between events. We do not measure time itself. There is no absolute now we can compare against. Only sequences, only memory, only records. If time were accelerating or decelerating very slowly, all processes would follow. Biology would adapt. Chemistry would adjust. Astronomy would recalibrate. The universe would remain internally consistent. And consistency is the strongest illusion of permanence. There is another layer to this problem. Change is defined as difference over time. If time itself is changing, then the metric by which change is judged is unstable. Change becomes self-referential. This means the universe could be evolving at a fundamental level without ever violating its own descriptions. The equations would still work. The predictions would still match, because the frame itself is evolving. This is not as strange as it sounds. Consider aging. You are constantly changing. Cells divide. Proteins fold and unfold. Neural patterns rewire. But from within your own experience, you feel continuous. The rate at which your internal processes change is your normal. Only external comparison reveals aging. Photographs, medical scans, long-term observation. The universe has no external photographer, no outside frame, no reference beyond itself, which means internal drift is undetectable unless it leaves imprints that survive time. This is where cosmology becomes relevant. The universe has a memory, radiation left over from its early state, light that has been traveling for billions of years, patterns frozen into large-scale structure. These are the only records not fully synchronized with the present. They are messages from earlier versions of the universe, and they tell us something intriguing. The early universe was different, hotter, denser, more uniform. That much is accepted. But the question is whether the difference stops at conditions or extends to parameters. Did time itself flow differently? Did constants behave differently? If time was moving at a different rate, then the evolution of constants might be inseparable from temporal evolution. Constants might not be drifting in time. They might be expressions of time. In this view, time is not a container for change. It is the mechanism of change. A slow release valve. As time passes, parameters relax, adjust, rebalance, not toward disorder, but toward coherence under expansion. This would mean that what we call now is not a fixed slice. It is a phase, a stage in an ongoing adjustment. Yesterday was a slightly different phase. Tomorrow will be another. Each close enough to feel identical, but none exactly the same. This idea challenges how we think about precision. We often imagine that better clocks bring us closer to truth, but better clocks may only bring us closer to coordination. They help us agree, not necessarily detect motion. If time itself is evolving, then precision instruments merely ride the evolution more smoothly. They do not resist it. They are carried. This has an unsettling implication. It means that the future cannot be perfectly predicted using constants measured today. Not because predictions are wrong, but because the parameters may not remain exactly what they are. Again, the change would be negligible on human timescales. Engineering tolerances would absorb it. Physics would remain functional, but deep extrapolations over billions of years would quietly diverge. And perhaps they already have. Some cosmological tensions hint at this. Measurements of the universe's expansion rate disagree depending on method. Early universe measurements and late universe measurements do not align perfectly. This discrepancy is known, debated, actively studied. It is framed as a problem to be solved. But what if it is not a problem? What if it is a symptom? A sign that the universe does not evolve on a single temporal rhythm. That time itself is not uniform across cosmic history. If time's behavior has shifted, then parameters derived under one temporal regime will not perfectly match those derived under another. The disagreement becomes meaningful, not noise, not error, but evidence of evolution. This would mean that asking whether constants change while we sleep is slightly misframed. The deeper question is whether sleep is our analogy for a process that never stops, a process so smooth that awareness cannot catch it in motion. The universe does not pause. It does not reset. It flows. And in that flow, today is never exactly the same as yesterday. Not because something dramatic happened, but because the underlying rhythm has advanced by one more imperceptible step, which brings us to a turning point. If time is part of the mechanism, then change is not accidental. It is built in. And if change is built in, then the universe may not be drifting aimlessly. It may be following a trajectory, a slow, constrained path through possible states. To understand that path, we must stop treating constants as isolated numbers. We must see them as components of a larger pattern, a pattern that reveals itself not in individual values, but in how those values relate to one another, because relationships can change even when appearances remain stable. And it is in those relationships that the next whisper waits. There is a reason this question keeps slipping away. Every time we think we have found a fixed point, it turns out to be moving with everything else. We look for an anchor, something that does not drift, something we can trust as a reference. But every candidate collapses under inspection. Rulers stretch with space. Clocks tick with atomic processes. Atomic processes depend on charge, mass, and interaction strength, which means the very tools we use to define unchanging are constructed from what we assume is unchanged. This is not a flaw in engineering. It is a limitation of being inside the system. When everything evolves together, the idea of a stationary reference becomes meaningless. Imagine a room where temperature increases uniformly. Every object expands slightly. Metal rods lengthen. Glass containers widen. Measuring tapes stretch. Inside that room, nothing appears to change. Only an outside observer would notice expansion. The universe has no outside observer, which means absolute change can occur without any internal contradiction. This is the quiet trap of synchronized evolution. It produces perfect internal agreement, and perfect internal agreement feels like truth. But it is only coherence. Physics, at its core, is relational. We measure differences, intervals, ratios. We do not measure absolutes. And when all absolutes drift together, only ratios remain stable. This gives us the illusion that nothing fundamental is happening, but something is. It just does not announce itself. This is why the question of changing constants has never led to a definitive answer. Not because the idea is wrong, but because the question is incomplete. We keep asking, is this constant changing? When we should be asking, what is everything changing relative to? If the answer is nothing, then the change is unobservable, not hidden, unobservable by principle. This is deeply uncomfortable. It suggests that there may be aspects of reality that are real, but forever beyond direct confirmation, not because they are metaphysical, but because they are relationally invisible. This challenges the quiet optimism at the heart of science, the belief that every truth is eventually accessible, given enough time, enough precision, enough ingenuity. But access requires contrast, and contrast requires asymmetry. If change is perfectly symmetric, access disappears. The universe becomes a closed conversation, speaking to itself, understanding itself, without ever revealing its motion to its inhabitants. This does not mean the universe is deceptive. It means it is self-consistent, and self-consistency is not the same as stillness. This realization reframes everything we have discussed so far. Gravity may be drifting, light speed may be adjusting, charges may be evolving, time may be flowing differently across eras, but none of these things can be isolated. They are coupled, linked, entangled at the level of parameters, which means the universe behaves less like a machine with fixed settings and more like a system that is continuously tuning itself, not randomly, not freely, within tight constraints. This tuning does not aim at perfection. It aims at coherence, a universe that stays understandable long enough for structure to form, long enough for stars to burn, long enough for life to ask questions. This is where the idea becomes almost philosophical. If the universe is tuning itself, then constants are not laws. They are agreements, temporary alignments between deeper variables, agreements that last long enough to feel eternal, but not guaranteed to remain. This changes the emotional tone of uncertainty. Uncertainty stops being a problem to eliminate. It becomes a feature to respect, because uncertainty may be the only window we have into evolution at the deepest level. Those tiny discrepancies, those stubborn error bars, those values that never quite settle, they are not signs of failure. They are traces of motion, the universe leaving fingerprints while trying not to disturb its own symmetry. From here, the question shifts again. If constants are agreements, then there must be a context in which they are negotiated. A deeper layer, where values are not numbers, but outcomes. Outcomes of conditions, outcomes of balance. To find that layer, we must stop focusing on what the constants are and begin asking why these constants exist at all. Why these numbers? Why this range? Why this coordination? Because coordination implies constraint, and constraint implies structure. A structure beneath the constants, a meta-framework, something that determines not the values, but the relationships between them. This is where physics begins to blur into something else. Not mysticism, not speculation, but a recognition of limits. We are reaching the edge of what can be asked within the language of fixed laws. Beyond this edge, questions do not vanish. They change form. They become about patterns instead of points, about evolution instead of snapshots, about becoming instead of being. And to move further, we must step back even more, away from numbers, away from constants, and toward the idea that the universe may not be described best by laws at all, but by tendencies, by attractors, by slow, guided motion through a space of possibilities. This is not how physics is usually taught, but it may be how physics truly behaves. And if that is the case, then the most important thing is not to find the final value of a constant, but to understand the direction it is quietly moving in, which means the next question is unavoidable. If the universe is moving through possible states, where did it start? And where is it slowly going? Because drift without direction is noise, but drift with direction is history. And history has consequences we have only begun to imagine. At some point, a quiet inversion occurs. We stop asking what the constants are and begin asking why they exist in this particular form. Because if the universe were governed by immutable laws, then constants would be axioms, given, untouchable, beyond explanation. But if constants are drifting, coordinated, constrained, synchronized, then they are not axioms. They are outcomes, the result of something deeper balancing itself. This is a subtle but profound shift. It means the universe is not built on numbers. Numbers emerge from the universe, and what emerges can change, not freely, not wildly, but conditionally. Physics already hints at this in ways we rarely dwell on. At extremely high energies, the forces we treat as distinct appear to merge. Electromagnetism and the weak force unify. At higher scales, strong force may join them. Gravity remains elusive, but theories attempt to include it. This tells us something important. The constants we measure today did not always exist in their current form. They crystallized. They emerged as the universe cooled. Symmetries broke, parameters settled. But settled does not necessarily mean stopped. In complex systems, settling often means entering a slow regime, a basin, a valley. Motion continues, but gently. This reframes constants as stable configurations rather than eternal truths. They are like climates, not laws. A climate can persist for millennia. It can feel permanent, but it is still the outcome of balance between deeper forces. If those deeper forces shift, the climate shifts, slowly. This analogy matters because it removes the shock from change. The universe does not betray its laws. It relaxes them, adjusts them, maintains coherence under new conditions. In this view, constants are not commands issued at the beginning of time. They are responses to expansion, responses to energy distribution, responses to entropy. The universe is not obeying laws. It is behaving, and behavior can evolve. This idea unsettles because it strips away finality. It suggests there is no ultimate equation waiting to be discovered, no last number that ends the search, only patterns that hold until they don't. But don't may mean billions of years, longer than any civilization, longer than any memory, which makes the distinction emotionally difficult to feel. We crave foundations, something that does not depend on anything else. But dependency may be fundamental. Even constants may depend. This dependency does not imply fragility. On the contrary, it implies resilience. A system that can adjust is harder to break than one that cannot. The universe may be robust because it is flexible, because it can slide its parameters rather than snap. This reframes fine-tuning. The universe appears delicately balanced. Small changes would destroy structure. This is often seen as miraculous, but in a self-adjusting system, fine-tuning is expected. The system resides in regions of parameter space where complexity is possible. When conditions drift, parameters drift to stay within those regions, not intentionally. Mechanically, like a ball rolling along a valley floor, it remains near equilibrium not because it is fixed, but because forces guide it back. This introduces the idea of attractors, states toward which systems naturally evolve. In such a framework, constants are coordinates of an attractor. They are not arbitrary. They are selected, not by design, by dynamics. This does not answer why the universe exists, but it does explain why it looks stable without being frozen. It also explains why constants appear correlated. If one changes, others adjust, because they are linked by the same underlying structure. This would explain why isolated change is never observed, why we never see one constant drift dramatically while others remain rigid. The system does not allow it. It corrects. This correction hides motion. Everything stays within bounds, which again makes change invisible from within. The implication is profound. We may be living inside a universe that is constantly repairing itself, not at the level of events, but at the level of parameters, tiny adjustments that keep complexity viable, keep stars burning, keep chemistry coherent, keep time flowing smoothly. And all of this happens without awareness, without signal, without announcement. This brings us back to sleep. When you sleep, your body does not follow instructions. It follows tendencies, homeostasis, balance, repair, correction. You do not tell your cells what to do. They respond to conditions. The universe may operate the same way. Constants may not be rules imposed on matter. They may be matter's response to the universe's state. This inversion changes how we interpret evidence. We stop looking for proof that constants are fixed and begin looking for patterns of stability, ranges, bounds, constraints. We ask not, is this number changing, but how far is it allowed to move? Because in a self-adjusting universe, freedom exists within limits. The constants we observe may be sitting comfortably inside those limits, drifting within them, never leaving, which is why we feel safe. This also suggests that the most dangerous question is not whether constants change, but whether they could ever leave their viable range, because that would mean the attractor has shifted. The valley has moved. The universe has entered a new phase. Such transitions may have happened before. During symmetry breaking, during inflation, during early epochs, we only glimpse through radiation. They may happen again, not violently, not suddenly, but gradually. So gradually that no generation would witness the boundary crossing. Only consequences accumulating long after. This is not a prophecy. It is a structural possibility, and it introduces a new way to think about the future. The future is not just what happens within the laws. It may be a slow reshaping of the laws, which means the universe has a kind of history we rarely acknowledge. Not just events, but evolving constraints, evolving possibilities. We often ask what will happen to matter, to stars, to galaxies, but we rarely ask what will happen to the numbers that govern them, because numbers feel eternal. But eternity may be an illusion created by slowness. If constants are outcomes, then the universe is not finished writing itself. It is still choosing, not consciously, but inevitably. Each moment narrowing possibilities, each adjustment shaping the next. This brings us to a deeper tension. If constants are emergent and evolving, then knowledge is provisional. Truth is time-bound. What is true now may not be true forever. And that does not weaken science. It humanizes it. Science becomes a dialogue with a moving reality, not a conquest of a static one. And dialogues require listening, especially to quiet changes, which leads us to the next step. If constants are outcomes of deeper dynamics, then those dynamics must leave traces, not in single values, but in how values respond to stress, to expansion, to imbalance, to perturbation. To understand that, we must ask how the universe reacts when pushed, how it resists, how it adapts, because response reveals structure, and structure reveals the rules beneath the rules. The ones that do not announce themselves as constants, but govern how constants are allowed to behave, and that is where the next whisper begins to take shape. There is a difference between a system that obeys rules and a system that resists collapse. Rules describe behavior, resistance reveals structure. If the constants of physics were rigid laws, then any deviation, no matter how small, would propagate unchecked. A slight change in gravity would distort orbits. A slight change in charge would unravel chemistry. A slight change in light speed would fracture causality. But that is not what we observe. The universe absorbs disturbances. It smooths them out. Local chaos does not cascade into global failure. Stars explode, yet galaxies endure. Fields fluctuate, yet averages persist. Energy redistributes, yet patterns remain. This resilience hints at something deeper than fixed law. It hints at regulation, not conscious regulation, not intentional correction, but dynamic response, a system that adjusts itself when pushed. This is familiar territory in complex systems. In ecosystems, populations fluctuate. Predators rise, prey fall. But feedback loops prevent runaway collapse. In physiology, blood pressure varies, temperature shifts, chemistry oscillates, yet homeostasis holds. These systems are not stable because nothing changes. They are stable because change is managed. If the universe behaves similarly, then constants are not brittle parameters. They are regulated ranges. They fluctuate within bounds. Those bounds are what we mistake for fixity. This would explain why constants appear finely tuned. They are not tuned once. They are continually maintained. This maintenance is not perfect. It allows small deviations, but it prevents catastrophic drift, which is why the universe feels forgiving. You can perturb it locally. You can add energy, remove mass, disturb fields, and still, the overall structure remains intact. If constants were truly rigid, the universe would be fragile. If they are regulated, the universe can breathe. This perspective changes how we interpret anomalies. Instead of seeing them as flaws, we see them as stress responses. A system reacting to imbalance. A slight discrepancy in measurement may reflect a transient adjustment. A small deviation may indicate the system nudging itself back toward coherence, not because it wants to, but because its structure enforces it. This introduces a powerful but quiet idea. The universe may have preferred states, not exact values. Regions, ranges, attractors. Constants hover near these attractors. They are pulled back when they stray, which would explain why long-term averages remain stable, why deviations do not accumulate freely, why everything changes, but nothing breaks. If this is true, then the universe is not drifting aimlessly. It is circling, slowly, like a pendulum with diminishing amplitude, always in motion, never settling completely. This reframes the meaning of cosmic history. The early universe was not a lawless chaos that suddenly froze into order. It was a phase far from equilibrium. As it expanded and cooled, it moved toward regulated regimes. Symmetries broke not to create rigidity, but to enable stability. The constants we observe today may be the result of that process continuing, not finished, just slowed. This also explains why radical changes appear to have happened early, and not now. Early on, the universe was far from equilibrium. Adjustments were large. Transitions were dramatic. Now, the universe is closer to its attractors. Adjustments are small, subtle, quiet, which is why modern physics feels stable, not because nothing is happening, but because what is happening is gentle. This gentleness hides activity, and hidden activity feels like stillness. Consider again the idea of sleep. During deep sleep, the brain is not inactive, it is highly active, but the activity is structured, purposeful, regulatory, repairing, consolidating. You wake up not because activity stops, but because the pattern of activity changes. The universe may be in a similar phase, an era of regulation, where the most important work happens beneath awareness, not producing spectacle, producing continuity. This raises a subtle question. If the universe regulates its constants, what triggers adjustment? In biological systems, regulation responds to deviation. Temperature rises, cooling mechanisms engage. Pressure drops, responses activate. What would be the analog at cosmic scales? Expansion, energy redistribution, entropy increase. As the universe expands, densities drop, interactions weaken, conditions change. To remain coherent, parameters may adjust, gravity may compensate, interaction strengths may rebalance, timescales may stretch, all in coordination. This would make constants sensitive to the state of the universe, not independent, not sovereign. They respond, which makes them more like variables than laws, but variables constrained by deep structure. This picture aligns with something we already accept. The laws of physics appear different at different energy scales. We already use different effective theories depending on conditions. The idea that constants might also be effective, valid within regimes, fits naturally. What feels radical is not the idea itself. It is the scale. We are extending this logic from laboratories to the universe itself, and from particles to time. If constants are regulated responses, then their apparent immutability is a byproduct of slow change. So slow that regulation never fails. So slow that no experiment catches the universe off guard. Which brings us back to a recurring tension. Science is built to detect failure, breakdowns, contradictions, but a perfectly regulated system avoids failure. It hides its adjustments inside tolerance. It keeps itself within bounds, which means the better the regulation, the harder it is to see. This is why the idea of changing constants remains speculative, not because it lacks motivation, but because the universe, if it is regulating itself, is doing an excellent job. Too good. This shifts our attention again. If regulation exists, it must leave signatures, not in values, but in correlations. How one parameter responds when another changes. How relationships remain stable even when components fluctuate. These correlations are subtle. They require large data sets, long time spans, comparisons across regimes. We are only beginning to collect such data, only beginning to notice tensions that do not go away, discrepancies that persist across methods, measurements that agree locally but disagree globally. These are not proof, but they are hints that the universe may not be static beneath its calm surface, that it may be constantly adjusting to remain what it is. This idea softens the fear of change. Change is no longer the enemy of order. It is the mechanism that preserves order. And if that is true, then the most unsettling possibility is not that constants are changing, it is that they must change. That stasis would be catastrophic, that a universe incapable of adjustment would fracture, which leads us to a strange inversion. What if constants are not fixed to protect the universe, but allowed to move to save it? If that is the case, then the universe is not a rigid machine. It is a living structure, not alive, but alive-like, responsive, adaptive, quietly self-maintaining. And if you listen closely, that maintenance may be what we have been hearing all along, not as a sound, not as a signal, but as the persistent absence of catastrophe, as the fact that night after night you go to sleep and wake up in a universe that still makes sense, even though it may not be exactly the same one you left behind. And this realization prepares us for the next question. If the universe is regulating itself, what happens when regulation fails? Not abruptly, not dramatically, but gradually, when the attractors shift, when the bounds move, when the conditions that allowed stability no longer apply, because regulation is not eternal. It depends on context, and contexts change, slowly, so slowly that the first signs are never obvious. They appear not as disaster, but as subtle tension, as numbers that no longer quite agree, as predictions that require ever more correction, as constants that feel slightly less constant than they used to, and that tension is already whispering. We just have not decided how to listen to it yet. There is a comforting myth hidden inside modern physics, that after the early chaos, the universe settled, that its deepest parameters cooled, locked into place, and have remained unchanged ever since. This myth is rarely stated explicitly. It is implied by equations that assume fixed constants, implied by models that extrapolate billions of years forward and backward using today's numbers. But implication is not evidence. And when we look carefully at the models themselves, something unexpected appears. Not all of them require frozen constants. Some of the most serious theoretical frameworks sometimes even require change. In certain cosmological models, constants evolve alongside the universe, not because they are unstable, but because stability itself demands evolution. In these models, the early universe did not merely cool, it transitioned through phases, through regimes where the effective laws of physics were different, forces unified and separated, symmetries emerged and broke. Constants did not descend fully formed. They crystallized gradually. This much is already accepted. What is less discussed is whether that crystallization ever truly finished, or whether it simply slowed to a pace we mistake for completion. There are theories where constants depend on scalar fields, fields that permeate space, fields that evolve over time. As these fields change, so do the values we measure. The change can be extraordinarily slow, so slow that over the lifetime of stars, nothing dramatic happens. But over cosmological timescales, the difference accumulates. In such a universe, constants are not numbers etched into existence. They are readings, like pressure or temperature. They tell us about the current state of the cosmos, and like all state variables, they are time-dependent. This idea feels radical only because we are used to treating constants as timeless. But physics already accepts time-dependent parameters in many contexts. The expansion rate of the universe changes. Energy densities evolve. Particle abundances shift. We accept these without discomfort. The discomfort arises only when change reaches what we emotionally classify as foundational. Because foundations are supposed to hold still. But what if the universe has no foundations in the way we imagine? What if it has processes instead? Processes that are slow, constrained, and deeply interdependent. In that case, constants are not foundations. They are footprints, traces left by deeper dynamics. This reframing solves a lingering puzzle. Why do constants appear so finely balanced? Why do tiny changes seem catastrophic? In a static view, this looks miraculous. In a dynamic view, it looks inevitable. If the universe passes through many possible configurations, only those that support structure persist. Others fade quickly. The constants we observe are not chosen. They are survivors. But survival does not imply immobility. A species can persist while evolving. So can a universe. There is another implication here. If constants are evolving, then different regions of the universe, especially regions separated by immense distances and times, may not share identical parameters. Not wildly different, but subtly. This opens the door to a more textured cosmos, a universe not perfectly uniform at the deepest level, but graded, layered, where conditions drift across vast scales. This idea aligns uncomfortably well with certain observations. Large-scale cosmic tensions, measurements that depend on early universe light disagreeing with late universe observations. These disagreements are often treated as technical problems, but they may be clues that the universe's parameters are not globally static, that what we measure locally reflects our epoch, not eternity. In this view, extrapolation becomes dangerous. When we project today's constants backward or forward indefinitely, we may be committing a category error. We are assuming timelessness where there may be evolution, and evolution does not reverse cleanly. It leaves scars. not dramatic ones. Subtle mismatches, persistent tensions. This perspective also explains why evidence for changing constants is always ambiguous, never decisive, because the change is small, because the change is distributed, because the change is entangled with time itself. The universe, if it is evolving its parameters, is doing so cautiously, as if constrained by the need to remain intelligible, as if dramatic shifts would tear coherence apart. So instead, it drifts, within narrow corridors, within allowed regions. This idea challenges our intuition about discovery. We expect discoveries to be sharp, clear, conclusive, but evolution does not announce itself. It whispers through trends, through statistical imbalances, through deviations that persist across contexts, and those whispers are easy to dismiss, especially when our tools are built to resolve snapshots, not trajectories. This is why the idea of unfrozen constants remains marginal. It does not fit into the experimental rhythms of modern science, which are fast, iterative, focused on short-term verification. Slow evolution demands a different posture: patience, memory, comparison across generations, civilizational continuity. We are only beginning to develop such capabilities. The earliest precise measurements of constants are barely a century old. That is nothing on cosmic timescales. We are trying to detect the movement of a glacier by watching it for a few seconds. Of course, it looks still, and so we conclude that it is, but glaciers move, slowly, relentlessly, shaping landscapes without spectacle. The universe may be doing something similar, shaping its own laws as it goes, not by rewriting them, but by letting them breathe. This brings us to a sobering realization. If constants are not frozen, then the future of the universe is not merely about stars burning out and galaxies drifting apart. It is about the slow reshaping of the rules that make stars and galaxies possible at all. This reshaping will not be violent. It will not announce itself with explosions. It will appear as continued normality, until, one day, the normality no longer supports what it once did. Not suddenly, gradually, so gradually that no observer can pinpoint the moment of transition, only the outcome, which raises the next question. If constants have not always been what they are now, and if they are still evolving, then there must have been periods when their values crossed important thresholds that changed what could exist. Those crossings may not be in our future. They may be behind us, or they may lie far ahead. But if they exist, they define the true history of the universe. Not the history of events, but the history of possibility itself. And to understand that history, we must ask not how the universe looks, but how it remembers. Because memory is what allows slow change to leave traces. And the universe has a memory, not in minds, not in records, but in structure, in patterns that persist long after the conditions that formed them have passed. Which means the next place to listen is not in numbers or equations, but in the silent imprints left by earlier versions of reality, imprints that still surround us, waiting to be read. Memory does not preserve motion. It preserves outcome. When you remember a childhood home, you do not remember every renovation, every repair, every slow shift in structure. You remember the shape that survived. The universe remembers in the same way. It does not store its past in timelines or records. It stores it in patterns, in structures that formed under conditions that no longer exist. Those structures are the only witnesses to what the universe used to be: galaxies, elemental abundances, background radiation, the distribution of matter on the largest scales. These are not snapshots, they are fossils, and fossils tell stories without explaining the process that created them. They reveal that something was different, not exactly how it changed, just that it did. The cosmic microwave background is often described as a photograph of the early universe, but this metaphor is misleading. Photographs freeze moments. The background radiation preserves relationships, tiny fluctuations in temperature, subtle variations in density, imprints of a universe operating under different constraints. We interpret these imprints using today's constants. We assume that the rules governing light, matter, and time have not changed, because without that assumption, interpretation becomes difficult. But difficulty is not disproof, it is discomfort. If constants have drifted, even slightly, then these ancient imprints were created under a different parameter set. Not radically different, but not identical, which means the universe's memory is encoded in a language that has subtly changed. We are translating an old dialect using modern grammar, and the translation works remarkably well, almost too well, until small discrepancies appear. Anisotropies that resist explanation, patterns that fit only after adding new ingredients, invisible components, additional assumptions. Each addition makes the translation smoother, but also more indirect. The universe's memory may be clearer than our interpretation. It is we who insist on reading it as if nothing fundamental has moved. There is another kind of memory written into existence: the relative abundance of elements. Hydrogen, helium, lithium, these ratios were set early. They depend sensitively on interaction strengths and expansion rates. Change those parameters even slightly, and the outcome shifts. The observed abundances match predictions within margins, always within margins. Those margins are celebrated as confirmation, but margins are also where drift hides. If the universe has been adjusting its constants slowly, then early nucleosynthesis occurred under slightly different rules. Rules close enough that today's models still work, but not exact. And again, the discrepancies are small, not enough to falsify, enough to question. The universe's memory is forgiving. It does not record every fluctuation. It preserves what endured, which means it cannot tell us whether constants were fixed or slowly evolving, only that they stayed within ranges that allowed structure to form. Memory is biased toward survival. This is why the past feels stable. Only the stable things leave traces. Everything else dissolves, which creates an illusion that what survived must have been immutable. But survival does not imply immobility. It implies compatibility. A changing universe can leave behind stable structures if change is slow and coordinated. Those structures then become anchors for interpretation. We project their stability backward. We assume the conditions that created them were the same as those that preserve them. But that assumption may be false. The universe's memory may be compressing its own history, smoothing transitions, hiding gradients, because memory preserves endpoints, not paths. This matters because it limits what evidence can tell us. We will never find a fossil that says, the constants were drifting. We will find fossils that look slightly strained, slightly mismatched, requiring explanation. And explanation always offers two choices: add complexity or relax assumptions. We have chosen complexity, dark components, extra fields, hidden dimensions. Each one preserves the idea that constants are fixed, that the universe remembers its past using the same language we speak today. But language evolves, even when meaning stays similar. A sentence written centuries ago can still be understood, but it is not written in the same grammar. The universe may be similar. Its memory speaks in a grammar that has shifted imperceptibly, which means we are always slightly mistranslating. This mistranslation is not catastrophic. It is subtle. It produces tensions, not contradictions, which is why the universe feels almost fully understood. Almost. This almost is important. It is the space where deeper truths hide. The universe's memory does not accuse us. It does not demand correction. It simply persists, quietly, asking whether our assumptions still apply. And as we move further from the conditions that created those memories, the translation becomes harder. The gap widens, not enough to alarm, enough to notice. This is where the feeling of unease in modern cosmology comes from. Not from ignorance, from overconfidence, from assuming that the present defines the past, when it may only approximate it. If constants are evolving, then the universe's memory is not wrong. It is just older than our language. And old languages require patience. They require listening. They require accepting that some meanings cannot be mapped exactly. This prepares us for a difficult realization. If the universe remembers differently than we measure, then our future predictions are also written in a dialect that has not yet fully formed. We project forward assuming stability, but stability may be conditional, maintained, regulated, not guaranteed, which means the future is not just a continuation of the present, it is a negotiation between expansion between entropy, between regulation, between slow drift, and negotiation implies limits, thresholds, points where balance shifts. Those shifts will not look like endings. They will look like subtle changes in what is possible, in what structures can persist, in what patterns can survive. The universe will not announce those shifts. It never has. It will leave traces, and those traces will become the memory for whatever comes next. This is not a reason for fear. It is a reason for humility. We are living inside a moment that feels permanent because we are synchronized with it. But permanence is a local experience, not a cosmic guarantee. As you listen now, you are surrounded by relics of earlier conditions, atoms forged under different rules, light emitted when the universe was younger, structures that carry the imprint of a reality that no longer exists exactly as it did. They still function, they still make sense, because change was slow, gentle, coordinated, which is why you are here to listen at all. This realization leads to a quiet shift in perspective. The question is no longer whether the constants are changing. It is whether change is the default state, and constancy is the illusion created by memory. If that is the case, then the universe is not aging towards stillness. It is aging towards something else, something we cannot yet describe using today's numbers. And to approach that thought, we must let go of the idea that the universe has a fixed destiny, because destiny assumes fixed rules. If rules can evolve, even slowly, then destiny dissolves into trajectory, a path that responds to conditions, a future that is not scripted, only constrained. And that realization brings us to the edge of the deepest discomfort. If the universe does not have fixed rules, then neither does meaning. Meaning becomes local, temporal, dependent on the state of reality itself, which raises the final, quiet question that waits beneath all the others. If the universe is slowly rewriting its own parameters, what does it mean to exist inside a story that has no permanent grammar? And how do we rest, knowing that even the rules of rest are part of the drift? That question does not need an answer yet. It only needs space. And that space is where the next whisper begins. There is a quiet coincidence hiding in plain sight. Human consciousness appears at a moment when the universe feels stable. Not frozen, not chaotic. Stable enough to be predictable. Stable enough to be studied. Stable enough to be mistaken for eternal. This coincidence is rarely questioned. We assume intelligence arose when conditions allowed it, but we rarely ask whether intelligence arose because conditions were changing slowly enough to hide their motion. If the universe were changing rapidly, awareness would be impossible. Perception requires continuity. Memory requires overlap. Identity requires gradualness. A world that rewrites itself too quickly cannot be inhabited by minds. So, if constants are drifting, they must be drifting slowly enough to allow observers to form, which means observers will always experience their era as stable. This is not a flaw in perception. It is a prerequisite for perception. The universe does not need to conspire. It only needs to change gently. Consider the timescale of human awareness. Seconds matter. Minutes blur. Hours dissolve into routine. Years compress into memory. Generations feel abstract. Cosmic timescales are beyond intuition. If a parameter drifts 1 part in a trillion per year, no organism could ever notice. But over 1 billion years, that drift becomes decisive. The universe can afford patience. We cannot. This asymmetry creates an illusion. We interpret our experience of stability as evidence of immutability. But stability is relative. It depends on the ratio between the rate of change and the rate of perception. Change slower than perception becomes invisible. Change faster than perception becomes chaos. Only within a narrow band does reality feel normal. We live inside that band, which means our very existence filters what kinds of change we can observe. This is a form of selection, not biological, epistemic. Only universes that change slowly enough can be known, and only minds that arise within those universes will call them stable. This reframes the question of constants entirely. It may not be that constants are fixed. It may be that only eras with slowly drifting constants can host observers. Every other regime passes unnoticed, not because it does not exist, but because nothing can exist within it long enough to ask questions. This idea is unsettling because it implies a bias built into knowledge itself. We do not see the universe as it is. We see the universe as it allows us to see it. Our theories are shaped by survivable conditions. Our assumptions are shaped by eras of tolerance. The fact that constants appear constant may say more about us than about them. We are tuned to slowness. We are blind to gradients. A fish does not feel the current of the ocean unless it changes abruptly. To the fish, water is still. Only storms reveal motion. The universe may be flowing constantly. We only notice when the flow accelerates. And perhaps those accelerations happened long before us. In the early universe, during phases when parameters shifted more dramatically, those were eras without observers, no memory, no testimony, only fossils. Now, the universe has slowed. Its parameters adjust with restraint, and consciousness becomes possible, which means consciousness is not a neutral observer. It is a product of cosmic gentleness. We are not witnessing a frozen universe. We are inhabiting a calm interval. This perspective dissolves a common fear. If constants are changing, why do we not feel endangered? Because danger requires thresholds, and thresholds are not crossed often. Most of the time, systems hover within safe regions. The universe may be far from any catastrophic boundary, drifting slowly, comfortably, which makes the present feel secure. But security is not permanence. It is positioning. We exist in a valley of parameter space, a region where stars burn steadily, where chemistry is rich, where time unfolds at a tolerable pace. The universe may wander within this valley for trillions of years, long enough that forever feels appropriate. But wandering is not stopping. This introduces a subtle humility. Our confidence in physical law may be misplaced, not because law is false, but because law is local, valid within regimes, stable within ranges, not universal in the timeless sense we imagine. The universe may not owe us eternal predictability. It only owes us continuity long enough to exist, and continuity does not imply immobility. This also reframes the role of sleep in our metaphor. Sleep is when awareness disengages. When change proceeds without narrative, the body does its work unnoticed. The universe may be doing the same thing. Most of its deepest adjustments happen beneath awareness, not because they are hidden, but because awareness is not designed to perceive them. This makes the phrase, "while you were sleeping," more than poetic. It is literal. The universe may be changing most effectively when nothing is watching, not because observation stops it, but because observation is irrelevant. Reality does not wait for witnesses. It does not need to announce its adjustments. It simply proceeds, and those who live within it experience the result as continuity. This explains why the idea of changing constants feels simultaneously disturbing and irrelevant. Disturbing intellectually, irrelevant experientially. Nothing feels different. Nothing breaks. Nothing demands response, which makes the question easy to postpone. But postponement is not resolution. It is deferral, and deferral accumulates over centuries, over civilizations, until tension builds, until anomalies multiply, until the assumption of stillness becomes harder to maintain. We may be approaching such a moment, not because change has accelerated, but because measurement has become sensitive enough to notice patterns that hint at slow evolution, at coordinated drift, at regulation rather than rigidity. We are not witnessing the beginning of change. We are witnessing the beginning of awareness. Awareness that what we called eternal may be conditional. And that realization is not dangerous. It is sobering. It suggests that knowledge must remain flexible. That understanding must be provisional. That certainty is a local experience, not a cosmic guarantee. As you listen now, you are part of this awareness, not as an alarm, not as a revelation, but as a quiet recognition that the universe you inhabit feels stable because it is gentle, not because it is finished. And if that is true, then the deepest question is not whether constants change. It is whether they ever stop changing. And if they do not, then the story of the universe is not a static script. It is a slow, unfolding conversation, one that does not rush, one that allows consciousness to appear, to listen, to wonder, and then, eventually, to fade. And that fading is not an end. It is simply the next phase of the same drift, which prepares us for the next thought. If change is inevitable and perception is limited, then perhaps the most important skill is not control, but attunement, learning how to rest inside a universe that is quietly becoming something else. And that is where the next whisper begins to soften even further. There comes a moment when measurement falls silent, not because nothing remains to be measured, but because measurement no longer knows what to compare. Science is powerful when there is contrast. This value versus that one, now versus then, prediction versus outcome. But if the universe is evolving its own frame of reference, contrast erodes. Everything moves together, and when everything moves together, explanation becomes circular. We reach this moment not with a bang, but with a pause. Equations still work. Experiments still agree. Technology still functions. And yet, something feels unresolved. Not wrong. Incomplete. This is not a failure of science. It is a boundary. Every method has one. Telescopes cannot see beyond the cosmic horizon. Microscopes cannot probe beneath certain scales. And measurement cannot escape a universe that carries its own rulers and clocks. When constants were assumed fixed, this boundary felt far away. But as soon as we allow the possibility of slow drift, the boundary moves closer. It reveals itself not as ignorance, but as symmetry. A symmetry too perfect to break from within. This is where science begins to sound like philosophy. Not because it loses rigor, but because it loses leverage. There is nothing left to push against. No stationary point to anchor explanation. Only patterns that hold. Only relationships that persist. Only regularities that slowly, patiently adjust. At this edge, the language of law starts to feel strained. Laws imply permanence. They imply obligation. But what if the universe is not obeying anything? What if it is simply continuing? Continuing along trajectories shaped by initial conditions, constraints, and feedback. No commandments. No violations. Just evolution. This thought dissolves a subtle arrogance. The idea that understanding means freezing reality into equations. Perhaps understanding, at the deepest level, means accepting that some things do not freeze. They flow, slowly enough to be intelligible, but not slow enough to stop. This does not diminish science. It humbles it. Science becomes a way of listening rather than commanding, a way of tracking rather than pinning down. At this boundary, questions change. We stop asking, what is the value? And start asking, what range is stable? We stop asking, is this constant changing? And start asking, what prevents it from changing too much? We stop asking, what law governs this? And start asking, what pattern persists? These are quieter questions. They do not lend themselves to headlines. They do not produce dramatic answers, but they may be closer to how reality actually behaves. There is a strange calm here. Once we accept that some aspects of the universe may be unobservable from within, anxiety fades. The pressure to solve everything dissolves. Not because mystery is comforting, but because mystery becomes structural, built in, expected. The universe does not owe us total transparency. It only owes us enough coherence to exist. And coherence does not require full accessibility. It requires smoothness. At this point, the metaphor of sleep becomes unavoidable. When you fall asleep, consciousness does not end. It loses grip. Processes continue, vital ones, but awareness withdraws. Not because it is excluded, but because it is not needed. The universe may not need to reveal its deepest adjustments to its inhabitants. Those adjustments do not concern daily survival. They concern long arcs, epochs, phases beyond any single narrative. To insist on witnessing them is to misunderstand scale. This is where the desire for certainty softens. The need to know whether constants are changing gives way to a different recognition. That even if they are, life continues. Meaning persists. Structure holds, which suggests that our fear of change may be misplaced. We fear change because we associate it with instability. But slow, coordinated change is not instability. It is maintenance. The universe may be maintaining itself, not forever, not perfectly, but long enough. Long enough for stars to form, for planets to cool, for chemistry to explore, for consciousness to flicker, and flickering consciousness does not need eternal laws. It needs gentle ones. At this edge, it becomes clear why this topic rarely surfaces in popular science. It does not offer control. It offers perspective. It does not promise mastery. It invites humility. And humility is not marketable, but it is restful. Rest comes from knowing what you do not need to hold, what you can let move. If constants are drifting, they are doing so without urgency, without threat, without intent. They are part of a system whose primary achievement is continuity. Continuity is not sameness. It is survival through change. As you listen now, nothing is demanded of you. There is no conclusion to reach, no belief to adopt, only a recognition that some questions are not meant to close. They are meant to remain open, like the night, like sleep, like the slow breathing of a universe that does not pause, but does not rush either. And in that breathing, awareness finds rest. Not because everything is understood, but because understanding is no longer required to feel at home. Which brings us to the final movement of this journey. Not a conclusion, not an answer, but a soft widening of perspective. If the universe is quietly adjusting itself, and if we are synchronized with those adjustments, then perhaps the most meaningful thing is not to catch the change, but to notice the stillness it produces, the stillness that allows us to exist at all. And that is where the last whispers begin to fade even further. There is a question that feels almost too quiet to ask. What if you have never woken up in the same universe twice? Not a different universe in the dramatic sense. No alternate histories. No branching timelines. Just not identical. So similar that memory stitches the difference shut. So continuous that identity remains intact. A universe that changes by an amount smaller than recognition. We already accept this idea in ourselves. You are not the same person you were yesterday. Not at the level of cells. Not at the level of chemistry. Not at the level of neural connections. And yet, you are. Continuity does not require sameness. It requires overlap. The universe may operate on the same principle. Each moment overlaps with the next, so completely that separation becomes meaningless. If constants drift, they do not jump. They slide. If time adjusts, it does not fracture. It stretches. If rules evolve, they do not announce themselves. They fade into the next configuration. From within, nothing feels different. From outside, if such a vantage existed, everything would be in motion. But there is no outside, which means the only experience possible is internal continuity. This is why the idea of change feels abstract. It does not show up in sensation. It does not disrupt routine. The sky looks the same. Matter behaves. Clocks tick. The universe performs familiarity flawlessly. But familiarity is not proof of identity. It is proof of smoothness. A smoothly changing system preserves experience. It allows narratives to continue. If the universe were to change abruptly, stories would break. Memory would fail. Causality would stutter. But none of that happens. So if change exists, it must be gentle. And gentleness hides motion. This brings us back to the phrase, constant. A constant is not defined by lack of change. It is defined by lack of detectable change. And detectability depends on scale, on comparison, on perspective. A mountain range is constant to a human life. A riverbed is constant to a generation. A coastline is constant to a civilization. None of these are truly constant. They simply move slower than attention. The universe may be the same. Its deepest parameters may be geological rather than instantaneous, moving on scales where awareness dissolves, which means the idea of waking up in a different universe is misleading. It is the same universe continuing itself, just not pausing. This reframes the fear of impermanence. Change is often imagined as loss, but slow change is not loss. It is continuation. The universe does not discard itself each night. It carries itself forward, minute adjustment by minute adjustment, never erasing what came before, only layering. This layered continuity may be the reason meaning survives. If everything reset completely, meaning would vanish. If nothing ever changed, meaning would stagnate. Meaning exists in the space between sameness and difference, between permanence and motion. The universe appears to inhabit that space perfectly, and so do we. This alignment is not accidental. We evolved inside this rhythm. Our minds mirror it. We notice abrupt changes. We ignore gradients. We remember endpoints. We forget transitions, which is why the universe feels stable, and why the idea of change feels theoretical. This does not make the idea false. It makes it subtle enough that it does not interfere with living, subtle enough that it allows sleep. Sleep is the ultimate acceptance of continuity without monitoring. You trust that when you close your eyes, the world will still be there, not because you have proof, but because experience has never contradicted it. The universe may trust itself the same way. It does not pause to verify its own consistency. It continues. If constants are drifting, they are drifting within a promise. The promise that tomorrow will resemble today closely enough to be navigable, not identical. Navigable, and navigability is all life requires. The fear that something fundamental might be changing often comes from imagining sudden collapse. But slow drift does not collapse. It adapts. It bends trajectories. It reshapes possibilities over immense spans of time. By the time consequences become visible, they feel natural, unremarkable, already incorporated into expectation. This is why revolutions in understanding often lag behind reality. Reality changes first. Understanding catches up later, sometimes much later. If we ever come to accept that constants have been evolving all along, it will not feel like a revelation. It will feel like a clarification, a quiet acknowledgement that we misunderstood stability, that we mistook coordination for immobility, and that misunderstanding did not harm us. It allowed us to function, to build, to explore. Now, perhaps, we are ready to let it go. Not urgently, not forcefully, gently, as one lets go of a childhood belief that no longer fits but once served a purpose. This acceptance does not demand action. It does not demand alarm. It does not demand belief. It only asks for comfort with uncertainty, comfort with the idea that you may never experience the universe exactly as it was before. And yet, you will always experience it as continuous, as familiar, as home. This is not a contradiction. It is a property of slow systems. They feel still while they move. As this thought settles, the focus shifts again, away from the universe as an object, toward the experience of being inside it. Because if reality is drifting imperceptibly, then perhaps the most meaningful question is not what is changing, but what it feels like to live within that change, to sleep inside it, to wake inside it, to age inside it, without ever needing to mark the motion. And that feeling, that quiet trust in continuity, may be the most fundamental constant of all, even if everything else is slowly, patiently becoming something else. Silence is often mistaken for absence, but silence is usually full of things happening too softly to interrupt. When a lake looks still, molecules are moving. When the night feels quiet, the planet is turning. When the universe appears calm, expansion continues. Stillness is a human word. It describes what does not disturb us, not what does not move. This distinction matters, because much of what we call constant may simply be what does not disturb perception. The universe has learned how to move without being felt. It has learned how to change without being noticed, not by hiding, but by moving evenly, smoothly, continuously. There is a kind of motion that creates no ripples. In physics, we call this symmetry. In experience, we call it normal. A perfectly synchronized system can evolve without producing internal friction. No stress, no break, no signal, which means the absence of sensation is not evidence of stasis. It is evidence of coordination. The universe, if it is changing its deepest parameters, is doing so in this coordinated way. Everything adjusts together. Nothing is left behind, which is why nothing complains. This is why the night sky does not feel unfamiliar, why matter behaves, why clocks agree, why sleep is possible. The universe has chosen smoothness over drama. not consciously, structurally, and smoothness is the enemy of detection. This is why we associate change with noise, with explosions, with disruption, but the most consequential changes in nature are often quiet. Continents shift beneath forests. Evolution reshapes species without announcement. Aging transforms bodies without a single moment of alarm. Only after long intervals do we notice outcomes, and even then, they feel inevitable. The universe may be aging in the same way, not deteriorating, not collapsing, just transitioning through states. The feeling of nothing happening is not a sign of cosmic boredom, it is a sign of balance. Balance requires movement, constant correction, tiny adjustments that cancel each other out. A perfectly balanced system is not static. It is busy, but its busyness is internal, invisible. This reframes how we should interpret calm. Calm is not the absence of process. It is the success of process. The universe has not paused its evolution. It has refined it, slowed it, smoothed it, until it became compatible with complexity, compatible with chemistry, compatible with memory, compatible with minds that wake up each morning and expect continuity, and receive it. This compatibility may be the most remarkable feature of reality. Not that the universe exists, but that it remains livable, that it does not lurch, that it does not fracture, that it allows stories to continue. If constants are changing, they are changing in service of this continuity, not to achieve a goal, but because continuity requires adaptation. As the universe expands, densities change. As densities change, interactions must rebalance. As interactions rebalance, parameters shift. The alternative would be instability. A universe that refuses to adjust would eventually tear itself apart. So change is not a flaw, it is a necessity. The stillness we perceive is the stillness of a system doing its job well. Like a heart that beats regularly, like a climate that remains within tolerable bounds, like a sleeper whose breathing remains even. We do not wake sleepers to ask if their lungs are moving. We trust the process. The universe invites the same trust. This trust is not naive. It is earned. Across billions of years of continuity, across the persistence of structure, across the fact that we are here at all, which brings us to a strange inversion. The question is not why the universe feels stable if things are changing. The question is why we ever expected change to be loud. That expectation comes from scale mismatch. From applying human intuition to cosmic processes, we are built to notice predators, storms, fractures, not gradients. Gradients require patience, and patience is rare, except in sleep. Sleep is when we allow gradients to work, healing, consolidation, recalibration. We do not supervise these processes. We let them happen. The universe may not require supervision either. Its deepest work may happen when nothing is paying attention, which makes awareness optional, not central, a side effect. This thought dissolves a subtle anxiety, the fear that if constants are changing, something must be wrong. No. If constants are changing and nothing feels wrong, then the system is functioning. Change without disturbance is health. Stasis without adaptation is brittleness. The universe appears healthy, resilient, which suggests that whatever adjustments are happening, they are not mistakes. They are responses to expansion, to entropy, to the slow unfolding of time. And responses do not need to be dramatic. They need to be sufficient. This reframes the final concern. If the universe is changing quietly, and we are synchronized with it, then there is nothing to do. No warning to issue, no correction to make, no action required, only awareness. And awareness does not demand vigilance. It allows rest. This is why this topic belongs in the quiet hours, not in debates, not in arguments, but in the space between waking and sleep, where the mind loosens its grip on certainty and allows the idea that some truths do not arrive as answers, but as atmospheres, as feelings of alignment, as the sense that things are moving without resistance. The universe may be moving, and the absence of resistance may be the point. As this realization settles, the narrative begins to thin, not because there is nothing left to say, but because saying less becomes more accurate. The closer we come to the edge, the quieter the language must become. Because The last movement of this journey is not about explanation. It is about release, releasing the need to know exactly how the universe holds itself together, releasing the need to freeze it into certainty, allowing it to breathe, allowing ourselves to breathe with it. And that breath carries us toward the final drift, not an ending, not a conclusion, just a soft opening where the universe continues, and we let ourselves continue with it, into the night, into sleep, into whatever comes next. There is a simple question we have not asked yet, not a scientific one, not a philosophical one, a practical one. If the universe is changing its deepest parameters, why is it doing so slowly? Not why in the sense of purpose, but why in the sense of consequence. Because speed matters. Change that happens too quickly erases structure. Change that happens too slowly becomes background. And the universe seems to have chosen the second option. Not perfectly slow, but slow enough. Slow enough that stars can burn for billions of years. Slow enough that planets can cool and stabilize. Slow enough that chemistry can explore possibilities. Slow enough that life can appear, struggle, adapt. Slow enough that consciousness can form memories. This slowness is not an accident. Not because the universe intended anything, but because only slowness allows persistence. A rapidly changing universe would not be violent. It would be impossible. Impossible to inhabit. Impossible to narrate. Impossible to remember. If constants drift, they must drift within limits set by survivability. Anything faster would tear coherence apart. Anything slower would be indistinguishable from stillness. The universe appears to operate at exactly this threshold, the boundary between motion and perception. The place where change happens without being felt, which is why it feels like nothing is happening at all. This reframes the emotional response to the idea. The fear that the rules might be changing comes from imagining instability. But instability requires mismatch, one part changing faster than another, one layer breaking synchronization. But everything we have considered points in the opposite direction. If change exists, it is shared, distributed, balanced. No component is left behind, which is why daily life proceeds uninterrupted. The sky does not flicker, matter does not misbehave, time does not stutter. The universe is polite. It does not disrupt its inhabitants with its own adjustments. It carries them along. This is an underappreciated kindness of scale, not intentional kindness, structural kindness, a consequence of continuity. The universe may not care whether we exist, but the way it exists makes our existence possible, and that may be enough. When we imagine cosmic change, we often imagine endings, the death of stars, the decay of matter, the cold future. But these are not abrupt. They unfold over spans that dwarf comprehension. They are slow, so slow that entire civilizations rise and vanish while nothing obvious changes. The same may be true of the rules themselves. They may not be eternal, but they are patient. Patience is what allows stories to unfold. Without patience, there is no plot, no development, no meaning. The universe may not be telling a story, but it behaves as if narrative length matters, as if transitions must be long enough to be lived through. This makes the idea of changing constants feel less threatening. It suggests that whatever evolution is happening, it is not racing toward collapse. It is drifting through viability, remaining within regions where structure persists, which means that for all practical purposes, for every breath you take, for every night you sleep, for every morning you wake, the universe remains usable, understandable, habitable. And that is not trivial. It is extraordinary. It also means that the present moment is not precarious. It is supported by a vast buffer of slowness, a margin of safety measured not in years, but in eons. This buffer gives rise to a strange calm, the realization that even if the deepest rules are not fixed, they are not fragile. They are resilient because they move, they adapt, they respond, which is what allows continuity. This does not mean the universe will always support complexity. No system does. Eventually, conditions will change enough that current structures cannot persist. But those transitions will not announce themselves in a single moment. They will unfold so gradually that no witness will experience them as endings. only as shifts in what is possible. This is already how the universe has always behaved. Stars do not suddenly stop working. They exhaust fuel over millions of years. Planets do not suddenly die. They cool, erode, transform. Life does not suddenly disappear. It evolves, migrates, adapts, fades. Why should the rules be any different? The rules may be part of the same continuum, evolving at a pace that respects continuity, which suggests a final inversion. The universe may not be stable despite change. It may be stable because of it. Change allows adjustment. Adjustment allows survival. Survival allows duration. And duration allows awareness. If constants were absolutely rigid, the universe would be brittle, unable to respond to expansion, unable to compensate for entropy, unable to maintain coherence. Flexibility may be the hidden reason anything lasts at all. This is not a conclusion. It is a reframing, a shift from fearing change to understanding its role, from demanding permanence to appreciating persistence. The universe persists. That is the fact that matters. As you listen now, nothing demands your attention. Nothing is breaking. Nothing is ending. The same universe that allowed you to fall asleep will allow you to wake up. Not because it is frozen, but because it is moving gently enough to carry you through. And that gentleness is not accidental. It is structural, which brings us quietly to the last space. Not a summary, not a takeaway, just a widening silence, where the universe continues its slow work, and you are free to rest inside it. Because whatever is changing, it is changing slowly enough for you to sleep. And that may be the most important constant of all. Nothing ends. Not really. Even endings are just places where attention stops following. Outside this moment, the universe continues. It does not wait for conclusions. It does not pause for understanding. It does not require acknowledgement. While you lie still, the planet turns. While your breathing slows, space expands. While thought loosens its grip, equations remain valid, or slowly, imperceptibly, become something else. Not in defiance of you. Without reference to you, the universe does not change for its inhabitants. It changes with them. Or perhaps it changes regardless, and inhabitants simply learn to float inside the change. This is the quietest possibility of all. That there is no moment when the universe decides to alter its rules. No switch. No announcement. Only continuity carrying itself forward. Minute adjustment layered upon minute adjustment. So smooth that even memory cannot find the seam. If the constants of physics are drifting, they are not leaving. They are transitioning. If time itself is evolving, it is not running away. It is unfolding. And if reality tomorrow is not identical to reality today, it is still close enough to feel like home. Home is not a fixed location. It is a region you can inhabit without strain. The universe may be nothing more than a vast homeostasis, always correcting, always balancing, always staying within ranges that allow itself to continue. And continuation is not stagnation. It is motion that does not tear. There is a kind of peace in this. Not the peace of certainty, but the peace of alignment. The sense that whatever is happening at the right scale, slow enough to allow rest, slow enough to allow meaning, slow enough to allow forgetting. Forgetting is important. If we remembered every micro change, we would never sleep. If we noticed every drift, we would never feel safe. The universe may forget itself in the same way, not storing exact states, only preserving relationships, only maintaining coherence, which is why it feels stable, which is why it feels trustworthy. Not because it is fixed, but because it is gentle. Tonight, there is nothing for you to solve, no theory to test, no belief to adopt. Whether the constants are changing or not makes no demand of you. They are not asking to be watched. They are not asking to be understood. They will continue whether you follow them or not. And perhaps that is the most restful thought. That the universe does not depend on vigilance. It does not collapse if you stop paying attention. It does not need to be held together by observation. It carries itself, as it always has, as it always will, for as long as always remains a meaningful word. If there is a difference between tonight and last night, it is smaller than thought, smaller than memory, smaller than fear. so small that it does not interrupt the rhythm. You are still here. The world still behaves. The sky still holds. Whatever is shifting in silence. And silence is not absence. It is space. A space where things can continue without friction, without urgency, without notice. As your awareness drifts, you do not leave the universe behind. You sink deeper into it, into the same continuity that allows stars to burn steadily and laws to feel reliable, even as they breathe. If tomorrow is not exactly today, it will still arrive gently, close enough, familiar enough, usable enough, and that is all reality has ever promised. Nothing more, nothing less. So, close your eyes. Let the universe do what it has always done. Move quietly, adjust patiently, remain coherent, and allow yourself to sleep inside a reality that does not need to be constant, to be kind.